all. On behalf of Kerala State Council for Science, Technology and Environment, I extend a warm welcome to all the participants to the 9th-month program conducted as part of Azadi Ka Amrit Mahotsav initiative of Government of India, the program being conducted to commemorate the 75 years of progressive India. The Department of Science and Technology, Government of India, and the state S&T councils have joined hands in organizing the 1 month, one theme initiative as Vigyan Utsav. The theme for this month is Future Technologies. Before moving to today's program, as usual, let's see a short video about Vigyan Utsav. Sunil, please.
15 अगस्त 2021 को भारत ने अपना 75वां स्वतंत्रता दिवस बड़े धूमधाम से मनाया और साथ में माननीय प्रधानमंत्री श्री नरेंद्र मोदी जी ने लाखों करोड़ों लोगों में नई ऊर्जा और चेतना जगाई। उसी चेतना को बढ़ाने के लिए देश के सभी विभाग विशेष कार्यक्रम का आयोजन कर रहे हैं। समाज के लिए विज्ञान और प्रौद्योगिकी विभाग द्वारा नावीन्य कार्यक्रम का आयोजन किया गया है, जिसका नाम है विज्ञान उत्सव। विज्ञान उत्सव कार्यक्रम सितंबर 2021 से अगस्त 2022 तक चलेगा, जिसे डिपार्टमेंट ऑफ साइंस और टेक्नोलॉजी गवर्नमेंट ऑफ इंडिया तथा स्टेट साइंस एंड टेक्नोलॉजी प्रोग्राम के तहत मनाया जाएगा। विज्ञान उत्सव कार्यक्रम में STI के लगते विषयों आधारित राज्य स्तर पर विभिन्न प्रकार की प्रवृत्तियां होंगी, जिसमें राज्य स्तर पर STI संस्थान, मानव क्षमता विकास, R&D इंफ्रास्ट्रक्चर, स्वदेशी प्रौद्योगिकी, नवाचार और स्टार्टअप, विज्ञान संचार और लोकप्रियता, महिला वैज्ञानिक, विज्ञान और समाज, फ्यूचर टेक्नोलॉजी, आत्मनिर्भरता के लिए बुनियादी विज्ञान, आत्मनिर्भरता और उद्योग और बौद्धिक संपदा अधिकार जैसे विषयों को शामिल किया गया है। विज्ञान उत्सव कार्यक्रम हमें आत्मनिर्भर भारत की ओर ले जाएगा। विज्ञान उत्सव में भारत के अलग अलग राज्य की विज्ञान प्रवृत्तियां और नवाचार के विभिन्न पहलू की झांकियों का प्रदर्शन करेंगे। इसी के साथ हम सब अपने आत्मविश्वास को आत्मनिर्भर भारत के लिए बुलंद करेंगे। इसे आप YouTube चैनल और SSTP के वेब पोर्टल पर देख सकते हैं। आइए आजादी का अमृत महोत्सव हम सब मिलकर विज्ञान उत्सव के साथ मनाएं। विज्ञान उत्सव हम सबका अपना उत्सव।
Welcome back. Let's move on to the program. May I invite Dr. S. Pradeep Kumar, the Member Secretary of Kerala State Council for Science, Technology and Environment, to welcome the distinguished guests and participants. Over to you, sir.
Thank you, Sharika. Professor KP Sudhir, Executive Vice President, Kerala S&T Council and Ex-Officio Principal Secretary, Department of Science and Technology, Government of Kerala. Dr. A.V. Rahul, from Civil and Environmental Engineering Department, Indian Institute of Technology, Tirupati. Professor B.J. Alapat from IIT Delhi. Dr. V.R. Sinija from Indian Institute of Food Processing Technology. Dr. A.P. James from Kerala University of Digital Sciences, Innovation and Technology. Dr. K. Satish Kumar, Department of Future Studies, University of Kerala. Sri Akhilesh, APJ Abdul Kalam Youth Challenge Program Awardee. And friends who are here representing iRove Technologies Private Limited, Ernakulam, and International Virtual Assistance Private Limited, Tirunandapuram, to share their experience of entrepreneurial journeys. Member secretaries and other officials of different state councils, directors, scientists, and other officials of different R&D organizations, Sri Arjun Prasad, Dr. Sherin, my dear colleagues, friends, and participants. A very good morning to one and all. Welcome back to the next session of the Azadi Ka Amrit Mahotsav, celebration of the 75th anniversary of Indian independence. We are again here to commemorate this monumental occasion we, the science and technology people, set our celebrations with the STA ecosystem with 1 month, one theme initiative for a resurgent Atmanirbhar Bharat. Today, we will be discussing about future technologies. The lead speakers and those who are here to share their vast experience will surely sail the ship to a different destination where the fascination of future technology awaits us. We all agree that the technology is rapidly improving, offering new innovations and revolutionary programs every year. At any given moment, scientists, engineers, and some very sharp minds are out there creating the new piece of future technology that will change our lives. It can feel like scientific progress is steady, but we have lived through a period of immense technological improvement in the last half century. Artificial intelligence and machine learning, robotic process automation, edge computing, quantum computing, virtual reality and augmented reality, 3D printing, Internet of Things, 5G, and many more technologies are at different levels of progress. Few are already implemented and in use, and all are also improving. It is time to ask how we can take full profit from the current technological revolution to reduce gaps that hold back truly inclusive and sustainable development. New technologies hold the promise of the future, from climate action and better health to more democratic and inclusive societies. Let me come back to my responsibility of welcoming the gathering. Professor K.P. Sudhir is the part and parcel of the Kerala State Council and leading the council at various levels. I welcome you, sir, to this program. Dr. A.V. Rahul, Civil and Environmental Engineering Department, Indian Institute of Technology, Tirupati, is the keynote speaker today. He has readily accepted our invitation and agreed to deliver the lecture on construction by concrete 3D printing, benefits and challenges. I cordially welcome you, sir, to this occasion. Professor B.J. Alapat from Civil Engineering Department, Indian Institute of Technology, Delhi, has agreed to share his vast experience in future technologies and achievements in solid waste management. I sincerely welcome you, sir, to this function.
Thank you. Thank you very much.
Dr. V.R. Sinija from the Food Processing Business Incubation Center in Indian Institute of Food Processing Technology will be discussing about emerging techniques in food sector. I welcome you to this function. Dr. A.P. James from Kerala University of Digital Sciences, Innovation and Technology has readily accepted our invitation and he will discuss about the intelligent 2D materials. I cordially welcome you, sir, to this function. Dr. K. Satish Kumar from Department of Future Studies, University of Kerala will address you with automated knowledge discovery. I sincerely welcome you to this function. Representatives of two agencies are here to share their experience: Aero Technologies Private Limited and International Virtual Assistance Private Limited. I sincerely welcome both of you to share your experience of entrepreneurial journeys. I sincerely welcome Dr. Datta, Dr. Reshmi, and Dr. Devikant from Department of Science and Technology, Government of India, to this function. I welcome all the member secretaries and officials of different state council, directors and scientists of various R&D organizations to this function. Sri Arjun Prasad coordinated this Kerala episode of Asadika Amrit Mahotsav. I congratulate him for the efforts and welcome to this function. I sincerely welcome all the participants who showed real interest in this program. I welcome and congratulate Dr. Sherin and Dr. Sharika, Sri Sunil and Jay Krishnan for their efforts for the successful conduct of this program. I welcome all my friends, colleagues, and all those who had gathered here to witness this function. Thank you. Thank you all once again.
Thank you, sir.
So Sharika, I think our principal secretary is not in a position to join this meeting. He is attending an official duty at Alappuzha. So connection problems are there. So we can move with the next program.
So we'll proceed with the program. Now, to detail the initiatives of Kerala State Council for Science, Technology and Environment, and the Government of Kerala initiatives in future technologies, I invite Sri Arjun Prasad, the scientist of KCSTE. Over to you, Arjun.
Thank you, Dr. Sharika. Let me share my slide.
Please move to the view mode.
Is it
Yes.
visible now?
Yes, okay, fine.
Thank you. So on behalf of KCSTE, I would like to welcome all of you to my presentation. So basically, it's as we all know, this month's theme is future technologies. And we are about to, I'm about to detail some of the initiatives of KCSTE and Government of Kerala in this area of future technologies.
Yes.
To find solutions for societal issues irrespective of their educational background. So under this scheme, KCST has supported an important project called Acute. Acute is curing technology to design a portable, simple, low-cost device for deaf people, which help them to hear the sounds with good clarity. So basically, this is an assistive technology which uses a bond conduction method. At the moment, the prototype has been developed and is now under the commercial product development phase. Another important scheme of KCST is partnering academic industrial research, which is a unique scheme which is focused on addressing the gap in translational research in science and technology, as well as skilled manpower for industrial requirement. So this is an important scheme which focuses on improving industry-academia relations. We have supported three major projects under this initiative. One is on the design and development of spectrophotometric systems for fast detection and quantification of lights. Then development of magnetic and automated magnetic nanoparticle-based purification system for biomolecules. And currently, one project is the running project, which is on the development of green adhesives for rubber to fabric and rubber to rubber applications. Another important scheme in the area of technology development is Technology Development Adaptation Program, which provides financial support and technical support for the development of new promising technologies and also for the adaptation of demand-driven technologies. An important few I'd like to discuss a few projects which were supported under the scheme focused on future technologies, which include design and development of a holographic data storage system, a bionic arm, then design and implementation of prototype Li-Fi system, which employs a visible light communication, and development of geopolymer-based construction products. Another important scheme of KCST is Emeritus Scientist Scheme, under which we are giving opportunity for superannuated outstanding scientists to conduct very promising and innovative research. Under this initiative, we have supported programs or projects on development of ready-to-eat combination meals in thermoformed containers using multi-layer films, and the sustainable second generation ethanol production technology for selected root and vegetables. And also in the area of food technology on the bioconversion of residues from major crops of Kerala and food processing to value-added organic resources for sustainable farming. Under the engineering technology program, which is aimed at supporting high-quality research in the field of engineering, we have supported projects including biodrying process, which is a sustainable technology for solid waste management, and early detection of breast cancer using mammographic images, then production of biodiesel from microalgae, and its investigation on its use in single-cylinder diesel engine, and the development of advanced fiber reinforced polymer nanocomposites for aircraft structure applications. Under the science research scheme, which is also aimed at promoting high quality research in fundamental and applied research, we have supported a project on development of a multi-wavelength integrating nephelometer for characterizing tropospheric aerosol, and also on apparatus, on the development of apparatus and process for the extraction of biopesticides from cassava bio-waste. KCST have initiated some new projects which include SRESTA, which is a state higher research centers of excellence in science, technology and applications, science and technology applications, which is to support high quality research centers to convert into centers of excellence in promising 5 areas, including water, biotechnology, nanotechnology, climate change, and robotics and artificial intelligence. So this is an opportunity to collaborate with a premier national or international research center, and fund will be provided to support and strengthen the institutional research capacity, and a financial grant limiting to rupees 200 lakh for a span of 5 years will be provided. Another important initiative is the digital research and innovation platform, where it's a web-based interactive platform to host various programs, and which it's a common facility, single facility to know about the different funding opportunities, technical resources available in Kerala. Another one is the STIRUP, which is science and technology intervention, incubation and research for raising startups in Kerala to support new innovative startups and innovative products. Another important new initiative is the scheme for promotion of interinstitutional research collaboration, which aims to promote a multidisciplinary research between a state R&D center or state institution with central institutions on projects which are socially relevant to Kerala. So a maximum grant of rupees 30 lakh will be provided for a span of 3 years. An important R&D center of KCST is the Center for Water Resource Development and Management. In the area of future technologies, they are in the process of, or they are in running a project which is focused on construction of wetland using nano phytoremediation for recycling of wastewater. So basically, it's a constructed wetland which is designed and operated to remove pollutants from municipal and industrial agricultural wastewaters using nanotechnology, electrophytoremediation, and microbes for enhancing heavy metal and pesticide removal efficiency. It's a part of a big project on integrated development plan for Calicut City, funded by UNDP, Nature, and DST. Integrated Rural Technology Center is a granting institution of KCST, and they are also involved in several innovative development of several innovative technologies, including crop residue biomass rapid composting, which is beneficial for the farmers. And they have established over 250 crop residue composting units in the district of Palakkad. They have also developed a recirculatory aquaculture system with moving bed biological reactor aquaponic system, a technology where water is recycled and reused after mechanical and biological filtration. And also it is used for high density culture of various species of fish utilizing minimum land area and water. Another one is the IRTC's microbial inoculum in solid waste management. It's a combination of safe bacteria, actinomycetes, and fungi with vibrant enzymatic activities. which has applications in leather industry and elephant waste composting. Now I would like to inform some of the new initiatives of Government of Kerala in the area of promising technologies, especially with a future impact. So in the present budget, many new projects have been proposed, which focus on focus on steps to boost the knowledge economy and linking skill with manufacturing. So a total of 4 science parks were envisaged and 14 district skill parks for young entrepreneurs to start their own ventures, a medical technology innovation center, a Kerala Genomic Data Center for Healthcare, 4 IT corridors along the South-North National Highway, 20 micro IT parks, a value-added agricultural mission, which is aimed at increasing the production of value-added products from agriculture. Now, a life science park, Tirunelveli, which is already established, and an Institute of Advanced Virology is already established there to work on promising technologies. A total budget of 2,000 crores have been set apart or proposed in this for the continuous or establishment of these projects. Another important initiative of Government of Kerala is on graphene. As we know, graphene is a remarkable substance on its own with a multitude of astonishing properties. It is the thinnest and most electrically and thermally conductive material in the world. Being very flexible, transparent, and incredibly strong, it has huge vast potential in the energy of medical field. So because of this huge potential, Government of Kerala is in the process of establishing India's first Graphene Innovation Center, which is a joint venture of the Digital University of Kerala, Center for Materials for Electronics Technology, Thrissur, and Tata Steel Limited. As we have seen, the Government of Kerala has numerous initiatives and programs to promote R&D and human resource development in the area of future technologies. Thank you.
Thank you so much, Arjun, for elaborating the initiatives of Government of Kerala and the initiatives of KCSTE in future technologies. Thank you. Now we have with us Dr. A.V. Rahul, the Assistant Professor in the Department of Civil and Environmental Engineering at Indian Institute of Technology, Tirupati, to deliver the keynote address on construction by concrete 3D printing, benefits and challenges. Dr. Rahul did his PhD from IIT Madras on the mixture development of concrete mixtures for extrusion-based 3D printing. Prior to joining IIT Tirupati, he was working as a postdoctoral researcher at McNeil Van Puyt Laboratory for Concrete Research, Ghent University, Belgium. There he was involved in the 3D 2B Green project, which focused on the construction of breakwater units in Dubai and Belgium ports using the concrete 3D printing technology. His primary research areas include concrete 3D printing, rheology of cement-based materials, cement hydration, and thermodynamics-based constitutive modeling. It's my pleasure to invite Dr. A.V. Rahul to deliver the keynote address. Over to you, sir.
Hello. Yeah. Thank you for the introduction. I'll share my screen. You can see my screen, all of you?
Yes, yes.
So good afternoon to all. I'll be talking about construction by concrete 3D printing. Primarily the benefits of concrete 3D printing, what it brings to the construction industry. Now, this being a new technology, it also comes with its own challenges. So how do you go past these challenges, and how you can where you can successfully implement this technology is what we'll briefly look at in this presentation. So this will be the outline of my presentation. I'll give an introduction about 3D printing, what is 3D printing in general. Then the more technical aspects of 3D printing from a civil engineering perspective. So how do you mixture design 3D printable concretes? What are the challenges pertaining to that? And then we talk about the actual benefits of 3D printing, and also some of the challenges involved in using this technology. And finally, we summarize the different aspects that we covered in this presentation. So starting with the introduction, concrete 3D printing. concrete printing, as you know, is at least if some of you have seen videos of concrete 3D printing, it's a method by which a structural element is made through a layer-wise deposition of a very special type of concrete. So that you can see it in this figure here. So you can see uniquely structured by deposition of concrete. So first a layer is extruded, then the nozzle through which this concrete is extruded out, that's horizontally upwards, and then another layer is deposited on top of that. So in this way, different layers are stacked. Hello, I can hear back my voice. There is some echo in the. Hello. Yeah, I think it's okay now. So in this way, different layers can be put on top of one another to make the entire structure. So again, why do we do this technology? One key aspect of this technology is the elimination of resources required to make a structural element. So you can reduce the labor. Another key aspect is the reduction in formwork. So for example, if you see this formwork here, this formwork is made in, if you see this column here, this column is about 1.5 meter height, and it was made in a very short duration of about 5 to 10 minutes and without any formwork. So if you compare this with how you would make this column conventionally, first you have to set up the form for this column, and then for setting up the form, you deploy resources. Then once the concrete is hardened, you have to remove the formwork. So many of these activities that you associate with conventional construction are being eliminated here. So because you eliminate these activities, you also eliminate the resources involved in these activities. And second is the huge difference in construction time that you can have. So here, as I said, to get this 1.5 meter high column with conventional concrete would definitely take a lot more time than what you would require with 3D printing. The other aspect is mostly brought out in this element here. If you see the shape of the structure, very complex shapes can be realized through concrete 3D printing. Why? Because when you do it through conventional methods, to make these complex elements require also very complex formwork, and especially to do thin elements, depositing concretes through these thin areas was also quite challenging. So making complex elements and also the elimination of resources and rapid construction becomes the key attraction with concrete 3D printing. Now, right from the point where this technology started being adopted, many countries around the world showed interest in this technology. So the first proposition of this idea happened around 1997, 1996. But a real push for this technology started in around 2012, where it was demonstrated at a laboratory scale that, in fact, concrete mixtures can be designed for this kind of technology for layer-wise deposition. Once this was demonstrated at a laboratory scale, a lot of people around the globe, if you see a lot of groups in Europe, a lot of groups in US, and even in Asia, if you see China, Singapore, India also has been involved in a few projects where they're trying to implement this technology. So a lot of countries around the world has shown keen interest, and it's not just the research group. Even if you look at from the industry side also, if you look at in Europe, for example, there are many startup companies who are focusing on this technology, trying to provide services specific to concrete 3D printing, specializing in this area now. So both industry and academia are showing have started. In fact, from the time that this was being introduced, both industry and academia had keen interest in taking up this technology. So some major projects that's happened around the world which has utilized this technology. On the top left, you see a barrack building that's made by the US Army. Now, the interest of US Army is another aspect concerning 3D printing, where you can do construction in inaccessible areas. So their idea is they transport the 3D printer there, and then they can set up a barrack building very quickly in areas where they can't really transport labor and other resources to the construction site. So construction in inaccessible areas is one of the focus which US Army is particularly taking this up for. And even Indian Army also has some projects where they're trying to make barrack buildings through concrete 3D printing technology. The second one that you see on the right side is called the Milestone Project, which involves construction of 5 residential houses. So here, the idea of constructing these houses, is to bring out the shape freedom that you get with 3D printing. So you can see this beautiful curves that's designed by the architects who made this building. So that's possible again because of the fact that you don't need formwork, and these complex shapes can be realized through niche technology like 3D printing. The third one that you see is set up in Italy, the project that was showcased in the Venice Biennale. So here it's a multi-leg pedestrian bridge actually, which was 3D printed. Different elements were 3D printed, and then they were assembled together. And the design was such that altogether the members act in pure compression. So then you eliminate the need to have reinforcement in the structure. Again, these arches and these unique shapes can be quite easily fabricated by concrete 3D printing technology. To do this through conventional methods, to do thin elements and to do curved elements through conventional methods would have been quite challenging. Then the one that you see on at the bottom is a project that's happened in Dubai, office building, which is right now at this point one of the largest building that has been 3D printed. It's about 640 meters square actually. This is an office building that's made in Dubai. So this printing, we'll talk about more technical aspects related to the mixture proportion and from a civil engineering perspective. One key aspect is how do you design the mixture for concrete 3D printing. Now, if it's even any type of 3D printing that you talk about, not just concrete, if you even talk about polymer 3D printing, what you need to really look at is to have a transition from a liquid-like to a solid-like behavior. So initially, to pump the concrete to the point where it has to be deposited. So you make a concrete and then you put it in a pump and then it has to be deposited through a nozzle. So first it has to be transported through to the nozzle, to the print head. So that point, till that point, you want the concrete to remain as a more liquid-like material. But once it's deposited out from the nozzle, once it's come out from the nozzle, the concrete should undergo a transition to a solid-like behavior. So in polymer printing, if you see, they do this transition based on temperature. So once the polymer is come out, it's quickly cooled. So it's inside the pump and inside the regions where it's being transported, it's heated to above its melting point. So it's like a liquid. Once it's exited from the nozzle, there's the sudden transition in temperature which causes it to transform quickly to a solid. In concrete, we use another aspect called, we work in a different way, how you do this through concrete, which I'll talk about in the coming slides. So two aspects that you need. One, the ability of concrete to be pumped up to the nozzle, which we call as extrudability in 3D printing terminology. And once it's deposited from the nozzle, it has to be able to retain its shape, or it has to have a solid-like behavior, which we call as buildability. So these are two essential requirements that you need to have, that you need to characterize to design mixtures for concrete 3D printing. So to achieve these characteristics, what we essentially work with is we generally work with the fluid behavior of concrete itself. So if you compare the behavior of, say, a water with a behavior of a fluid like concrete, what essentially stands out is concrete is a Bingham plastic type of material. So in Bingham plastic type of material, if you see in this graph here, some initial stress has to be reached before the flow has to be initiated. If you see the graph for Newtonian fluid, even at very small shears, even when you apply very small shear stress, you can see a flow initiating in the material, or you see that there's rate of shear strain happening in the material. But in Bingham plastic material, certain stress level, you can see that through the non-zero y-intercept here, certain shear stress has to be exceeded for flow to initiate in the material. Now, once the flow has started in the material, the slope of the graph will dictate the resistance to flow, or the viscosity, or how much resistance there is to flow, which we call as the viscosity of the fluid. So the graph of this line would determine the viscosity of the Newtonian fluid, and the graph of this line will dictate the viscosity of the Bingham plastic fluid. Now, to design concrete for 3D printing, to have that shape retaining characteristics, we have to design concrete to have a high yield stress. To give a comparison, for conventional concrete, you would normally have an yield stress of around maybe 200 pascals, 300 pascals, in that range usually. But for printable concrete, you have to have an yield stress about 1,500 to 2,000 pascals. So about an order of magnitude higher than that you would have for a conventional concrete. So this high yield stress ensures that even once the material is pushed out from the nozzle, once there's less stress on the material, the flow is prevented in the material and it is able to retain its shape. But during pumping, we use a specially designed pump to go above its yield stress, and then to initiate flow in the fluid. So we use specially designed pump to pump this high yield stress concrete. But once it's deposited out from the nozzle, the high yield stress ensures that the concrete can retain its shape. Now, another aspect also that we need to understand is what happens or what type of failure that can happen in a freshly printed concrete. So once the concrete is printed out, what type of failures can occur in the printed element? So here we need to distinguish between two types of failures. One is a plastic collapse, and the other is a buckling collapse. Now, plastic collapse happens. You can see it in this figure here, and there's too much stress exerted on the bottom layer. The bottom layer starts to flow, and there's plastic collapse occurring in the material. Buckling type of collapse occur in the case of thin elements. If you have very thin elements, then it can undergo lateral deformations due to buckling, and then the element can undergo a buckling failure. Now, if you look at buckling equations that we derive for hardened concrete, the same would apply here. So there, if you see the material parameter that influences the resistance to buckling is the elastic modulus. So the material should have sufficiently high elastic modulus once it's deposited to prevent buckling type of failure if you're especially designing or if you're especially looking at very thin elements. Now, here again, buckling failure will also depend on the section properties or the moment of inertia. For example, if you have a printed element with high moment of inertia, that will provide a higher resistance to buckling failure. And also the cross-sectional area, even sectional properties will also influence, and also the density of concrete. That will also influence the resistance to buckling failure. Now, with this, I mean, having understood that there's elastic modulus and as well as the compressive strength, both these parameters influencing plastic and elastic type failure, plastic and buckling type failure in fresh concrete. Now, how do you characterize these properties? Now, in hardened concrete, there are standardized methods to do this, but how do you characterize this for a fresh concrete? So here, this is an experiment that shows how to do this. So this experiment essentially works on doing a uniaxial compression test on fresh concrete. So concrete is cast and it's immediately demolded. So you can see this immediately demolded concrete here. So this is cast and it's just 5 minutes of age, this concrete. So the reason, because there's a high yield stress for this early age concrete, for 3D printable concrete, it's more stiffer than the conventional concrete. Even when you demold it, it can still retain its shape. Then we do this test with a very sensitive load cell, a very low load cell we use to carry out this test. And we capture deformation using a video extensometer system. And in fact, you can do this test with different time intervals. So here you can see that the maximum value is increasing as a time interval proceeds. And you can also see it from 240 to 420 minutes. And the other aspect is the type of failure also. Because initially you see an elastic behavior and then a plastic type deformation after that. So it's mostly an elastoplastic material early on, but as you proceed to higher ages, as you go to 420 minutes, for example, you see more of a strain softening type behavior, which is most closely associated to that of hardened concrete. In fact, that you can also see in how the specimen fails. So this is how a specimen would fail when it's at 0 minutes. It's mostly a very plastic material. It can have some elastic strain carry capacity. And then after that, it undergoes plastic deformation, or fails by undergoing indefinite plastic deformation. But in the hardened concrete, you see that there's enough rigidity formed in the structure. There's some network of hydrates that has started to form, especially if you look at 420 minutes or 5 to 7 hours in that range. Then you will see that there's some rigid hydrate network that's formed from the formation of hydrates. And the breakage of hydrate results in the formation of shear cracks. And that, in fact, leads to the strain softening plans that you see here. Now, the slope of these graphs, now here you're looking at stress displacement, but you can convert that to stress strain graph. And if you take the slope of that graph, you can capture the elastic modulus. And the maximum stress that you see in this graph, you can capture the compressive strength. And if you do it at different time intervals, if you do it at different, cast the specimen and do it after different rest duration, you can see the evolution of compressive strength. And similarly, you can see the evolution of elastic modulus. So both of these parameters then can be utilized in models to look at whether the print element that you're going to do is actually going to fail by plastic collapse, or at what height it's going to fail at plastic collapse, or what height it's going to undergo a buckling collapse. These calculations can be run to ensure that you don't undergo a print failure when you actually carry out the printing process, when you actually do the printing process. Just to give you also some brief info about the mixture design. Now, there are no standardized codes or procedures, as you can imagine, but you can definitely look at approaches like particle packing to design 3D printable mixtures. And also in 3D printable concretes, when you choose a certain type of ingredients to include in the mix design, you have to always think of how it's going to influence the flow behavior or the rheology of the system. Say, for example, if you add additives like microsilica and nano clay they're likely to decrease your setting time. So you will see a much more rapid evolution of compressive strength and rapid evolution of elastic modulus. So when your mixes incorporating nanoclay or microsilica, you can carry out the printing much faster, because now the evolution of the material parameters occur much faster. Also, if you sometimes during pumping, you can encounter issues like phase separation, which you can avoid by using admixtures like methyl cellulose. And robustness is another key aspect also you need to consider in mix design. One problem with 3D printable concrete is the range over which it actually works is very narrow. Especially if you have a batch change in one of the materials. For example, you're using a particular type of fly ash, and the batch of fly ash that you're using has changed now, then you might see some change in the workability of the concrete because of this batch change. And that workability change may be just sufficient to cause the mixture not to print properly. So that range over which, or that robustness range you have with these kind of mixers is very narrow. So how do you address this issue is also something that we need to look at. In fact, studies have indicated that certain chemical admixtures like methyl cellulose can be introduced, which can in fact provide a wider range, or the mixer becomes mixer is able to remain printable over a wider range and show more robustness when you incorporate these type of admixtures. So this is also an important aspect that we need to consider when you perform the mix design. Now, to address the question is, where do you use this technology? What type of structures that you can actually make with 3D printing technology? Some of this we looked at in a slide earlier, where we saw some of the major projects happening around the world. But to generalize, one aspect where 3D printing has to become, where you have to look at 3D printing is when you're particularly to do a complex structure. Now, why do you need to do a complex structure is also there. What advantage you get from a complex structure? But before that, just to give you the comparison of cost. So if you have a more complex structure, as complexity increases, so here you can see this dark line shows the conventional concrete, and this dotted line shows that you obtain through digital fabrication. So if you are looking at less complex structure, mostly a rectilinear type of structure, then you see that because the mixture cost for 3D printing is quite high, you will see that digital fabrication may be quite more costlier than conventional concrete. But when you have cases, when you have some more complexity in the structure, let's say you have to do a curved element, or you have to do some other complex type of geometries. So there you see that the conventional construction becomes significantly more expensive. That's because you have to have a form to do this type of structure, and then the former cost significantly adds to the total construction cost. But when you have digital fabrication or 3D printed structure, you don't have that significant increase even when the complexity of the structure increases. So there's a break-even point, and above that you can see that conventional concrete is significantly more expensive than concrete made through digital fabrication. And right now the cost is quite high, but then there are a lot of research happening around the world, including in India, where we are trying to bring down this cost by looking at less costlier and less more viable type of additives in designing the 3D printable concrete. So with this break-even point can be, through further research, this break-even point can be shifted further downwards, where then 3D printing becomes also more economical in relatively less complex structure. The same also applies for market value. For complex structures, if you see, with the dark line indicating conventional concrete, there's very little market value for very complex structures. But for 3D printing, the market value is still higher, even when you have very complex structure. So another aspect we need to talk about is why do we need to do complex structure? So one aspect with complex structures is that now you can actually do shape optimization, and through shape optimization, an overall reduction in material volume can be achieved to meet the same to have the same structural performance. So an example is shown here. So here you have a simply supported beam actually. Now, if you want to remove elements or remove the volume of material from regions where it's not really required, you want to optimize your structure. So this can be done through various softwares like topological optimization based softwares. Then you can end up with a skeleton like this. And the dark color actually represents where you really require the material, and the material in the other regions can be subtracted out. But then to really make this complex type of structure is really very difficult in real life scenario because of the formwork involved. But with 3D printing, this can be done quite easily, and with introducing that complexity, significant material volume reduction can be achieved. So that then brings in the sustainability element in 3D printing. So this is a bridge that was made at Ghent University in Belgium. So here this is a topological optimization algorithm carried out to design this post-tension bridge. And here you can again see that complex shape that was achieved from the topological optimization. So it was divided into different elements, and these elements were separately printed and then assembled and held together by post-tensioning. The other added advantage is also the functionality that you can get with 3D printing. Say, for example, if you talk of countries where you have cold weather, like in Europe and even America, or countries like Canada, so their ability to your thermal conductivity also becomes an important parameter in building designs. So here you can see a 3D printed panel being compared to conventional concrete block, and here you can see that it offers a significantly lower thermal conductivity, so that indicating that it's quite favorable for constructions like this, and it's more closer to an insulating material as compared to your more commonly used construction materials in this part of the world. And one more aspect that you can do is with is to use functionally graded materials. So through 3D printing, you can use different type of concretes in different regions. Again, if you come back to the beam example, let's say if you have a simply supported beam, in the central region where you have the maximum bending moment, there you can do it with a high strength concrete. And in the other regions, another nozzle can be used to print maybe relatively low grade concrete, which would be much more lesser expensive rather than using the same material throughout the beam. So that sort of approaches and that sort of elements can also be made using construction 3D printing. Now, before we wind up this presentation, I'll also just give a few aspects regarding a project that I worked in. So this project is called the 3D2B Green project, which is carried out at the Ghent University in Belgium. So this project is to construct breakwater units using the 3D printing technology, and this is in collaboration with some of the industries, one of the major construction companies in Belgium, and there are two other companies, Resourceful and Vitavine plus Bose, which are also involved in this project. So the aim of this project was to use 3D printing technology to use breakwater units and deploy in Belgium as well as Dubai ports. Now, why particularly breakwater units? Why do we choose 3D printing for breakwater units? Now that you can also understand the complexity in the shape of breakwater units. Some of the elements being shown here. So they have very complex shapes, breakwater units, to meet the hydraulic performance. So there again, utilizing this technology can be significantly, can bring quite a lot of economic benefits. So reduce formwork costs, because again, these elements, if you look at these complex elements, they have to be cast in specially made formworks. So especially given the fact that you have to have several numbers of these breakwater units, several number of these units, having so many number of formworks or waiting for one form to be concrete to be released from one form to cast the next one, so that introduces significant delay in construction, which leads to an overall cost increase. So there, if you can actually do 3D printing, in fact, an in situ 3D printing, a robot where if it can be brought to the construction site and then made and can be printed very close to the where it has to be deployed itself. So that offers significant economic benefits when analysis was performed, when an initially feasibility study was done. So the complexity of shape, reduced formwork costs, and also some preliminary studies that we did at the lab also indicated that the layered structure the 3D printing has may provide for additional energy dissipation, therefore providing for a better better hydraulic performance when you compare mold cast with 3D printing, and also the possibility for on-site 3D printing, bringing down the transportation cost in such cases. One more aspect that I'd like to talk about is a set-on-demand type approach. This is a patented approach which was also developed at the same university. Now, here we try to introduce an accelerator at the nozzle to increase the buildability of concrete. Now, in 3D printing, there are several conflicting requirements. One of the conflicting requirements is that between extrusion and buildability. So, for good extrusion, for the concrete to be easily pumped up to the nozzle, it has to be as flowable as you can. But once it has exited from the nozzle, it should have a very low workability. It should stiffen very quickly so that you can build more layers on top of that. So the material requirement before extrusion and after extrusion conflict with each other. So therefore, because of this, we are often restricted to, either if you actually make it very stiff, then you will end up with pumping issue. If you make it too flowable, you will end up with issues on buildability. So most of the time in 3D printing, you are restricted with the height that you can reach. So in fact, here you can see from the scale, if you look at a person standing it's just reached half of its leg. So it's about maybe 0.3 meter or 0.4 meters in height. And after that, you can see that the structure started to collapse. In fact, you can see it's undergoing significant plastic deformation at this stage. But on the right hand side, here we work on a technique called set out demand, where an accelerator is introduced just at the nozzle, which significantly alters the stiffening rate of the concrete. So the introduction of this accelerator causes it to undergo a flash set. And this allows us to make much larger structures. So here, this column is about 1.5 meter, and it's showing no signs of failure until now. And this was made in at a very rapid construction speed. In fact, this was printed at 4 times faster as compared to the first element. So the higher rate that you can also achieve, and also the higher height that you can achieve with this technology, is also one aspect one advantage with the set on demand type approach. So to summarize what we looked at in this presentation, so we discussed why 3D printing is a promising technology for the construction. There are certain niche areas or certain domains where 3D printing can be significantly more economical as compared to conventional construction. Then we talked about the technical aspects, the challenges in designing the 3D printable concrete. But these challenges can be surpassed if you really understand the science of what aspects you need to look at. The aspects before deposition and the aspect after deposition, and what type of test methods you can design, which can help in developing or formulating 3D printable concrete mixtures. Then where 3D printing becomes economical, primarily in making complex structure, and also in areas where elimination of formwork or formwork itself contributes significantly to the construction cost. Then finally, we talked about an ongoing project called 3D to be green, which is being done at Ghent University, which works on developing sustainable 3D printable mixes for construction of breakwater units. Yeah, so with this, I wind up the presentation. Yeah, if there's any questions that you want to ask me, you can ask me. Just 1 second, Larry.
Any questions? Hello, sir. I think there are no questions. So
Yeah.
thank you so much for giving us a perspective on the technology of 3D printing and also its applications in construction with insights from your ongoing urban the project. I think Ajit Prabhu sir is having a question, sir, please. I can see your hands raised. Hello, sir. Okay. Hello, Ajit sir. Do you have a question?
Sir, I think you're muted.
Yeah, there was some technical problem. I was trying to unmute it, but it was not going unmute. That is the problem. Yeah,
Okay,
I am Dr. Ajit Prabhu, Chief Scientist in KSCSTE. I have a small doubt in the sense,
yes.
What about how you are controlling the scalability factor for 3D printing? How
Sir,
you are accommodating? Yeah,
scalability
factor.
means
Yeah.
from going small scale to large scale elements.
Yeah, because from small objects to big objects, so that scalability factor, how you are accommodating?
Yeah, sir, I'll just share my screen once again. Yeah, sir. So here we can do it through 2 approaches actually. So if you see the bridge here, so there how it's being done is the larger element is printed by combining many small elements. So it's quite, you can see it visible here. So this is the size of one element. So, but the structure as such is quite large. So the large scale element is made through printing small elements and then assembling on site. The other approach is to do it in one go. So that type of approach was done in the office building in Dubai. So here the height is about 9.5 meters nearly. So here a very large size robot, the company that was involved was called Aptiscope. So they are a very large 3D printed robot. So that was brought to the site, and it was done in 2 print sessions actually. So one where it reached half the height, and waited for some time for the concrete to harden, and then the remaining part of the structure was made. So the scalability issue is dealt in 2 ways. One, that we make small elements and assemble to get the larger element. Other is that we use a larger concrete 3D printer itself, and then try to do it in one go.
Okay, that is fine. But my specific doubt is, once you join pieces, what about the force dynamics? You know.
Yeah. So here
how
in
that
this
will be
case,
taken care of? Yeah.
so in this case, so this aspect is an important element actually. How do you do the connections? So there we have to, when we design the structure itself, we have to keep in mind how to do that. So here in this case, what they did was, because when you assemble everything, this was in pure compression, you don't need bed connections in the structure. So it had to be just put in place. But on the other hand, there are tensile members in this, then there'll be a stretching at the joints, and then you need to have some joining at the connection itself. So in this way, that was taken care here. Another approach is, if you do here, if you come back to this bridge here, so here the connection itself was ensured. There is grout connections between the different elements, but the connection itself was ensured by the fact that this is a pre-stressed element. So a pre-stressed, a strand is put in place, and that pre-stressing force ensures that it's held compactly together. So that's an important element, how to design the connection. In terms of compression elements, you can stack them and just join it using some using a grout or any type of mixture that's designed as a joining material. Or otherwise, in the design stage itself, you have to accommodate for this. Ensure, like, when you have pure compression, you don't need bed connections. You can provide, but it's not really essential. Or you do, when you're doing beam elements, you can do pre-tensioning. In this way, the connection is ensured.
Yeah, fine. But what about the reliability aspects? Because when more number of pieces are joined together, reliability also maybe R1 plus R2 plus R3, like that it goes, no?
Yeah,
so
that element is still there, correct? So
yeah,
that regard, we have to look at more studies in that regard. In terms of statistical and reliability analysis.
yes.
Yeah.
Okay, thank you, Professor. Thank you.
Thank you, sir.
I think there are no more questions. Thank you so much, sir. Thank you for your address.
Thank you for having me in the session also. Thank you so much.
Thank you.
Thanks.
And
I'll leave the session.
If you want, you can wait also, sir. Otherwise, you can leave.
Yeah.
We have a few more speakers too.
Then thanks.
Okay, thank you so much. Now we have Professor B.J. Alapat, who is a professor of environmental engineering in the Department of Civil Engineering, Indian Institute of Technology, Delhi. He got his PhD in environmental engineering from IIT Bombay and postdoc from École des Mines Nates, France. He has more than 24 years of teaching and research experience in environmental engineering. Professor Alapat specializes in environmental engineering, especially on waste management, incineration techniques, and fluidized bed reactors. He has published more than 170 research papers in international and national journals and conferences. He is a reviewer of more than 20 international journals, also has guided several PhD and MTech projects. He is a consultant to many governmental and non-governmental organizations and expert member in several committees. His main contributions in waste management include incineration, in recirculating fluidized bed reactors, waste to energy, environmental indices like incinerability index, landfill pollution potential index, leachate pollution index, etc. It's indeed my pleasure to invite Professor B.J. Alapat for the invited time. Sir, please.
Thank you, Dr. Sariga. Let me share the slide. Now, can you see the?
No,
Can you see the
it's
slide now?
coming.
It's coming.
Yeah, it's
Now you
fine.
can move to the view mode. Now you can
You
move
can
to the
make
view
it in the
mode.
full screen, sir. Otherwise, okay.
I'm just trying. This is
Okay.
fine.
Now it's okay.
Okay, okay. So thank you very much. First of all, good morning, and we are in between good morning and good afternoon. Thank you so much for inviting me. A special thanks to Professor Sudhir and Professor Arjun Prasad, who was communicating with me, and also to all authorities of Kerala State Council. I could see many known people sitting there. Professor Ajit Prabhu, sorry, Dr. Ajit Prabhu, Dr. Harinarayanan. So namaskaram to everybody. Today, I just thought of speaking to you about the developments and the advancements that has been happening in the area of municipal solid waste management, and also something about the future technologies that may come in application. In this small PPT of 15 minutes, I will touch upon some of the policy aspects that has changed recently, some of the technical aspects, some of the philosophical aspects, and of course, on the monitoring and waste assessment side. And let me tell you in the beginning, there is no any single shot solution for waste management, especially when it comes to municipal solid waste management. There is no any machine that will consume plenty of municipal solid waste and give you one golden biscuit maybe at the end of 1 month. There is nothing like that. See, to tell you about the advancements, I should tell you what was happening long ago in 1950s and 1960s. Do you know the municipalities and the corporation used to collect raw mixed municipal solid waste, raw mixed MSW, and just take it out of the city boundary and you dump it. That is why we have many land dumps. And once upon a time, they were all outside. Lalur of Trishur, and even Delhi, we have 3 huge land dumps. I'll show you some of the pictures. So what happened? These were outside the city boundary long ago. And by 1980s, 1990, you can see city grew like anything. And the land dumps are actually now within the city. And this is true for all the cities, the Thapa dumping grounds of Calcutta, the Okela, Ghazipur, Balsora dumping grounds of New Delhi, even the Devanar dumping ground of Bombay. So then the problem starts because many people start living very close to the land dumps. As you can guess, there will be leachate pollution problem, particulate issues and landfill gas issues. So government understood that there should be some intervention. Before the MSW is dumped, there should be some intervention like MSW treatment. And, windrow composting facility, refuse derived fuel making facility, even some incineration facility all came up addressing this fact. The idea is to minimize the waste that is going to the land dump and also to reduce the biodegradability or to use these waste and go for something to recover, So you can see we start with the storage of municipal solid waste, transportation of municipal solid waste, treatment of municipal solid waste, and the final dumping or final landfilling. You can see advancements have been happening across all these domains. For example, about storage, do you know very interesting containers started coming recently? It has all facilities. When you go nearby, it opens on its own and it will compact on its own. It will tell you what you have put and it will give you some points. Maybe you can encash it in big bazaar or elsewhere, I don't know. So these kind of ATM kind of waste banking things. So these are the smart containers which are likely to come up in future. And I know a lot of research has been happening in this direction, but I have not come across a smart container with all these features. That is why I am not showing any pictures or anything. Similarly, coming to the municipal solid waste collection facility, nowadays the collection facilities are, the collection vehicles are with GPS and all navigation system. Once upon a time we had only just trucks and tractors. Now we have self-loading, compacting, modern facilities with all GPS and all kind of things. So this is a dumper place, dumper placer carrying the container. And in Delhi we have an array of vehicles because some areas are actually highly congested. So normal vehicles will not go there. So you can see we in Delhi, I'm sure in big cities like Trivandrum or in Cochin, you will be having an array of collection vehicles. And you can see things have improved like anything. Look at the street sweeping. Manual street sweeping is giving way to the mechanical street sweeping. Maybe 10 years ago, you must have seen only in the airport, some machinery will come and they will try to, sweep the floor. Now it is on the road. If you come to Delhi, you can see street sweeping on the road. So things are changing a lot. Then, in 2000, this rule book came, the first rule book on municipal solid waste management. And it's very interesting. And as per the rule, it says waste has to be processed before landfilling. And no more land dumping, but only engineered landfills. But as you can guess, no engineered landfills came up in the country for MSW. Even now, we have only very few engineered landfills. We call it sanitary landfill, SLF, for municipal solid waste. But there are a few for hazardous waste. We call it secure landfill. So here the interesting part is the technologies started competing with each other because they are all dealing with the same raw mixed MSW. And people started comparing with composting and incineration, whether incineration is better or composting is better. Actually, it is like comparing jackfruit and apple. Both are fruits only, but they are quite different, is it not? So the technologies actually started, competing with each other, and people started comparing all these technologies. And the issue and the outcome was poor quality compost, very low quality RDF, and refuse derived fuel, and relatively lower performance of the waste to energy facilities. Then came the rules of 2016, which emphasized the need to segregate the waste right at the source. So we are recommending, not we are recommending, already recommended, the green container for biodegradable waste, the blue or white container for dry waste, recyclable waste, and hazardous waste will be going to the black container. And it's very clearly written, biodegradable components of the MSW should not be burned. It should go for any bioprocessing, composting, vermicomposting, or biomethanation, anything, but not burning. So this is a big difference in the philosophical approach in dealing with MSW. And the dry waste containing different components will be going for sorting and separation. And the combustible part can go for incineration or RDF making or for any other thermal technique like gasification or plasma pyrolytic technique, etc., etc. And the surprising and the interesting thing is, for the first time, there is a mention about how to deal with used sanitary pads and napkins. Everyone knows it's a very, very burning issue, right from Trivandrum to Jammu and Kashmir. But we never used to address that. In 2016, at least something was told about that. So here now, because of this intervention, the technologies have become now complementary. So this is the philosophical difference I want to highlight. The technologies like composting and thermal techniques, they have become brothers and sisters, complementary to each other. So this is a major deviation. And the question is, can't we separate right at the source? As you know, it may not be having in the big city, but in some of the cities like Indore, Surat, Vijayawada, etc., and some of the states like our own state, Kerala, there are a lot of emphasis on the segregation right at the source. And you must have seen, I'm sure about it, you must have seen pot composting facility, bucket composting facility, pipe composting facility. These are all with the intention to deal with the biodegradable portion of the MSW right at the source. I know there are some issues with some of these facilities, but if you know the theory behind it, you can make it operational. And please understand, this is not at all any rocket science or missile technology. This is very simple common sense and knowing the fundamentals of the technology we are using. So the issue is, from waste to good quality compost, it takes a long time. That is the key. I'm very glad to see that some of the projects are running in Kerala on accelerating the speed of composting. I listened to, I think, Dr. Arjun Prasad in the beginning. So very nice to see that in Kerala we are addressing that issue. So the idea is to bring down the time requirement for composting. And there are different techniques by different pre-treatment. Things are coming down. The time requirement is coming down. And the problem with composting is you don't get a good quality compost because we start with all mixed waste. Please understand, waste once mixed, you cannot separate them completely. And the most dangerous component to be separated is actually our food waste. If food waste is getting mixed up with the rest of the components, then you are going to have it. Because food waste will be always contaminated and you cannot change it. You cannot separate it. You cannot separate it using any technique that are available properly. That is the issue. Similarly, biomethanation is a technology which are implemented. I know there are many biomethanation plants in Kerala. And some of them are working well, some of them are not working well. But please understand that small biomethanation plants can be made to work properly, but not very large plants. There are some very large plants in indoor 150 tons per day. There are huge plants working now, but their performance is not up to the mark. A lot of research has to be done in that direction. Similarly, what to do with this lignocellulosic material like garden trimmings, agro waste, etc. I could hear that there was a project being given in that direction in Kerala. That's very good. And lignocellulose material, you cannot actually mix it with, you can mix it, but the kinetics are very different. If you compare the kitchen waste and lignocellulosic material, the kinetics are very different, kinetics of biodegradation. So normally these kind of things actually need pre-treatment. As you know, in New Delhi, in the month of October, November, we have huge, severe pollution because of the stubble burning. So a lot of work is going on in that direction also. Then, as I told you, only mixed waste is, unfortunately, mixed waste is a reality in most of the cities across the country, especially big cities. And how to deal with that? The interesting part is the municipality has to go for very complex facilities now. This is the Okala incineration plant set up in 2016. It was actually set up to burn raw mixed MSW. But the moment rules were implemented, they cannot burn the biodegradable matter. So you can see there is an array of separation techniques like magnetic separator, eddy current separator. There are, screens. And finally, they do some composting and they do some incineration and they get compost and they get energy. So that is what I told you. If we don't segregate at the source, then the municipality will be forced to segregate in their plant. And the incineration plants are becoming now integrated waste management facilities. Once we segregate the waste, then everyone knows what to do. I know a good job is happening in Kerala. We all know what is happening once the segregation is happening, once it is separated. And these days, lots of emphasis is given on the waste preparation. You cannot dump a waste just like that. You cannot treat a waste just like that. So waste treatment or waste pre-treatment is getting a lot of attention. Waste drying and removal of stone and glass and other inert components and blending with some high heat containing material. And do you know in bio drying, how to dry MSW? There is something called bio drying, and some very good contribution has come from Cochin University in Kerala. In this kind of bio drying, what they do is they try to use the first part of the aerobic composting. There will be thermophilic microorganisms releasing a lot of heat, and that heat is actually used to dry the MSW. So a lot of things are happening in the pre-treatment, like drying, and also on the separation side. There are many separation techniques because we don't separate it at the source. So many cities are actually starting to fine the people because they don't segregate. I'm sure there will be very soon fine implemented on the people who are not actually separating the waste properly. So you can see there is an array of separation techniques which are nowadays used by the municipality. And there are magnetic separators and eddy current separators to separate the non-ferrous metals, and there are sensor-based separation system. And I can tell you, the sensor-based sorting is receiving a lot of attention these days. And we have three techniques: near infrared range sensors, visible light spectrum sensors, and LIBS using a laser. So this NIR, near infrared range sorting facility, will use these kind of waves, and there is a sensor. And the moment they sense that something is coming, normally it is used for separating paper and cardboard and these kind of things, packings and these kind of things. And a steam jet or an air jet will push it to the side. Similarly, people are using visible light using camera. So these are all already implemented. But something is very interesting. This visible light is normally used for separating different kind of glasses. Clear glass, brown glass, green glass, like that. Then another technique is LIBS, laser induced breakdown spectrometry, spectroscopy. Here, there is a laser beam injected onto the waste, and there will be some emission which will be sensed. And any plastic like PVC or PU, it can be sensed and it can be removed. So this is something which I want to highlight because, when we teach, we say, do not burn polychlorinated plastics like PVC. it will generate dioxin and furane. So don't burn PVC. But how do you separate PVC? So there are techniques. This is one of the techniques which are yet to be implemented commercially on a big scale. But I'm sure there is a lot of scope in removing PVC from the bulk of the MSW that is burned. Then coming to waste to energy scenario, nowadays from the waste to the grid power, the efficiency, conversion efficiency is very, very low. It is just 20 to 23% from waste to the grid power, the electricity. Another issue is, so a lot of research is happening in this direction to improve the conversion efficiency of the waste to the grid power. Similarly, there are air pollutants like dioxin and furane, which are actually very toxic. And the unfortunate thing is, you cannot actually sense it. Nowadays, most of the people use sensors for HCl, NOx, SOx, all these, all these gases, CO, CO2, all these gases are actually sensed. Pollutants are sensed. But sensing will not work for dioxin and furane, which are actually very, very dangerous carcinogenic compounds. So we need to take a sample, take it to the GCMS or whatever is the instrument. So that is another challenge. If you can, eradicate dioxin and furane, or you can sense it, that I'm sure you can become a billionaire, if not a billionaire. Similarly, bottom ash. In all developed nations, their fly ash is dangerous. But bottom ash, they are using for different construction. Construction like, road construction, embankment and whatnot. But in India, we have seen that our bottom ash is not inert. I don't want to say it is hazardous, but we have to take it with a pinch of salt. We have to see that whether it is inert or not. It's not inert. Fly ash is dangerous in most of the scenario. So as I rightly told you, separation of PVC is an issue. So I don't want to spend time on all these things. And just to highlight one point, how to destroy use sanitary napkins and pads. I'm telling you, this is an issue which has to be addressed by all the municipalities and corporations and panchayat very, very soon. Already, I think they are making some small incineration facility. But if somebody can make a small instrument which can be carried by any lady in her bag, and it can destroy the napkin without any pollution, I'm sure it has great commercial potential. Similarly, the last thing I want to tell you is about the landfilling, the last entity of solid waste management. It's a very costly affair. And the whole treatment, the idea is to minimize the waste that is going to the landfill. As you know, we had only land dumps. And now we are actually moving towards engineered landfills. This is a land dump from New Delhi. I don't know how many of you remember. There was a slide of just 150 tons per day of MSW. One day it slided. You can see 150 tons per day slided. And the whole thing fell into one canal here, and two cars were pushed into the next canal, and I think 4 or 5 people lost their life. Very embarrassing thing for New Delhi. This is a picture from our Cochin land dump. So land dumps are giving way to landfills, engineered landfills now. So this is the cross section showing you the concept of engineered landfill. There should be proper liner bottom, and there should be proper cover, and water is not allowed inside, and water is not allowed to escape also. So water is actually collected. The leachate is collected from the bottom, and the landfill gas is collected from the top. So this is called an engineered landfill. If it is meant for dumping municipal solid waste, it is called sanitary landfills. And nowadays, actually, people are going towards bioreactor landfill. So the entire landfill is viewed as a huge bioreactor. So what they do, they collect the leachate from the bottom and recirculate it. So we can reuse this landfill area again and again and again after maybe 8 to 10 years. So these are all upcoming areas of research and commercialization of the technology. And now everyone speaks about landfill mining. In New Delhi, we are also trying to mine that old mountains of MSW. But what to do with the mined material? It's a valid question. If there are plastic, you can take it for burning. But what about the inert, which are huge in amount? So can you use it for road making? Can you use it for construction? It has a lot of organic matter present. That is the issue. So a lot of research is happening in that direction also. Similarly, another issue is public acceptability. I'll wind up in another 1 or 2 minutes. Public acceptability is a very big issue because any waste management facility, people, NIMBY syndrome, not in my backyard syndrome, banana syndrome, build absolutely nothing anywhere near anything or anyone, banana syndrome. So I don't want a waste facility to come up in my backyard. It can be in your backyard. But what is the solution? Because see, the population density is going higher and higher. There is only one way, in my opinion: involve people right from the beginning, right from the planning stage, and maintain transparency. So, as the last point, which technology is going to sustain when we speak about MSW or waste management technology? Let me tell you, in my opinion, the technology that can be integrated with the urban utility services may be the one that may survive. It need not be necessarily the most eco-friendly one. It need not be necessarily the least priced one. But those technology which can be integrated with the power grid, integrated with the construction industry, integrated with the agriculture, Indian urban scenario is a very, very complex scenario. Can you tell me how many urban systems are here? You can see power distribution, you can see communication lines, you can see residences, you can see commercial establishments, and below the ground, you can, water supply line, wastewater sewerage line, even solid waste collection facility. So it's a must to integrate all these things, and that technology which can be integrated nicely, in my opinion, those technologies may be the one that may sustain. So that's all from my side. I just conclude telling that there are a lot of challenges, a lot of opportunities in dealing with municipal solid waste. And I know there are many young people listening to me, and a lot of ideas should come from you. Because when you are young, you get a lot of very good ideas. You get into the fundamentals, and whatever ideas you get, don't waste it. Okay, you can contact the state council, or you already got some briefing from the authorities. So do not waste your ideas. They are actually very, very valuable. It may not get back to you later. So that's all from my side. I think now there are a lot of changes in the municipal solid waste management. The technologies have become now complementary to each other, and the concept of integrated waste management facility already established. So that's all from my side. Once again, I thank you for inviting me for this lecture. I'm sorry that I could not complete it in 15 minutes. I tried my level best, but spilled over. I'm sorry for this. So you can avoid questions so that the time is maintained up to some extent.
Thank you so much, sir, for that enlightening address. I think there are no questions. You have elaborated on the different approaches and technologies in solid waste management. And thank you so much.
Professor
Now,
Alapat,
Yeah, Professor, yes.
to see you and
Yes,
listen
sir.
to
What do you
your
say?
expert talk. Yes. I have a couple of doubts in the sense.
Yeah,
See,
you
one
can go
is,
ahead. No problem.
One is some years before, it was actually considered that the plasma arc gasification (PAC) process was somewhat like an advanced system used in Japan and other countries, and I guess some plan came in Madras, Chennai also, but
Yes.
subsequently nothing is heard about that. So I
Yeah,
want
I
to
can tell
know
you.
details about that, whether it is practically feasible, can
Yeah,
it be considered as a future technology?
sir.
Number one.
Yeah.
Number
Professor,
two,
I
what
can tell
about
you.
thermoelectric generators? From incinerators, actually heat is getting really wasted. So how
Yeah.
can we usefully convert it into electricity? So these are
Yeah.
two doubts I have.
Yeah.
Yeah.
Okay. So the first question, I'm very glad that you asked this question, because actually I had a couple of slides on plasma pyrolytic reactors, which I removed actually, because I thought I would spill over beyond 15 minutes. So do you know, in IIT Delhi, we are actually installing a plasma reactor right now. So in IIT Delhi, actually I can tell you, as a technology, there is nothing wrong. Actually, it's a good technology because you get a syngas, you get a fuel gas, and the fuel gas can be used. Theoretically, it can be compressed and used. So what we are doing here in IIT is we are actually trying to burn all our non-biodegradable waste. It is only to the tune of 1 to 2 tons per day, 1.5 tons per day. And the problem is, if you do not have a continuous supply of power, then please don't go for this technology, because this technology is highly power intensive, as I understand, highly power intensive. And one good thing is it gives you an ash, which is actually molten. So the ash to be disposed of, the quantity is very less. So there are some plus points with this. But I will never recommend this technology on a very large commercial scale in India at the moment, because we do have problem with the continuous power. Even in Delhi, we are facing power shortage now. But small plant, yes, it can work. And why we are making this plant? Actually, the construction is going on right now in IT Delhi. Why we are doing it? Because the biodegradable portion we are taking care of by composting, maybe composting facility we have. But actually, we are outsourcing this non-biodegradable like plastic and paper and leather, textile, etc., paying some money. So we thought we will put up a plant costing around 1 crore. So that we can generate some syngas and do some research. But on a commercial scale, we have to be careful, Ajit sir. So it can be used very nicely for biomedical waste. Because normally for biomedical waste or hazardous waste, the quantity generated is little bit, not much, maybe 100 kilogram or 50 kilogram per day. But the moment you speak about MSW, it goes to 200 tons, 2000 tons. So it's not a good idea.
Yes, yes.
Then coming to the second question, actually waste is burned, flue gas is generated, and there is a heat exchanger to exchange the heat from flue gas to the water becoming steam, and steam runs the turbine, and turbine runs the generator, and generator produces the power to the grid. So you are very, very correct that there are so many units involved which actually create huge loss of energy. So what people are doing now, they will be actually trying to recuperate. Once the steam is made, the flue gas still has got a lot of heat. So they construct more than one heat exchangers. So the main heat exchanger is to produce superheated steam, maybe 400 degree, 40 bars steam. The very first, in the initial stage, they try to make good quality steam. Normally it is 40 bars, 400 degree centigrade steam. And after making this steam, you should not let the flue gas go out. You can have couple of more heat exchangers to preheat the combustion air or to make hot water like that. So there are many trials have happened. Instead of making hot water, suppose you go to some of the cold nation, you can see super heated water being circulated for heating the room and the rooms and other things. So instead of making steam, a portion of the flue gas is actually used to make hot water, super critical, super heated water. So you are right. At the moment, the efficiency is very low, but there are ways and means to improve. But of course, one has to pay for it.
Professor, precisely, rather than going to steam generation and then to electricity, there is actually a direct conversion system, like that Seebeck effect, and with the thermal difference, electricity can be produced.
Would you repeat?
See, the directly, the thermal difference, the heat generated, and like that Seebeck effect, electricity can be produced.
But which is the technology? It is there is no turbines involved.
I heard such technologies are available, but I'm not aware about any plants that are available. So that avoids, this loss of efficiency and all steam generation and nothing like that. Directly, that heat tapped from that point, and two dissimilar metals joined at two different temperatures will produce electricity.
Okay, that is the principle of thermocouple. Okay, based on the principle of thermocouple.
Method.
I have no idea. Yes, I have no idea. I have no idea. But I understood the theory behind it.
Okay.
Anyway, this must be an upcoming technology, but not commercially available at the moment.
Also, but I'm not sure practically whether it is done somewhere.
No, I have not come across, sir.
Okay.
Normally, if it is implemented somewhere, we come to know. So I doubt. But theoretically, it's possible. Theoretically, it is possible because it's the same principle of thermocouple.
Thermocouple effect. Yes. Thank you.
Okay.
Thank you so much, sir.
Yeah, thank you very much.
Now we have Professor Sinija, who is the professor and head at Food Processing Business Incubation Center and chair, Center of Excellence in Non-Thermal Processing at National Institute of Food Technology, Entrepreneurship and Management, Tanjavur, who was the institute which is formerly known as the Indian Institute of Food Processing Technology. She has acquired her PhD and MTech degrees in Agriculture and Food Engineering from Indian Institute of Technology, Kharagpur, after her BTech in Agriculture Engineering from Kerala Agriculture University. She has nearly 18 years of teaching and research experience in the field of food processing. a member of Academic Council, Board of Studies, Board of Examinations of various institutions across the country, has more than 75 peer-reviewed journal publications, and received Professor Jeevan Singh Sidhu Award for the year 2018 by the Association of Food Scientists and Technologists for teaching excellency, and similar many such awards. As the head of Food Processing Business Incubation Center, she has coordinated more than 500 skill development training programs, and more than 100 budding entrepreneurs have successfully set up their food processing business through this skill development program and consultancy services. It is indeed my pleasure to invite Professor Sinija for the invited talk. Ma'am, please.
Thank you, Dr. Sarika. Let me share my slides. Hope my slides are visible.
It's coming,
It's
ma'am.
coming, downloading.
Okay, so good afternoon, everyone. Thank you very much, Professor Sudhir, Dr. Arjun, and all the organizers for giving this opportunity. So before going into this topic, emerging techniques and the future trends in food processing, let me first tell about what is the present scenario of the Indian food processing sector now. Actually, the food processing sector, India's food and grocery market is the 6th largest in the world, and which is contributing nearly 14% of the total industrial output. And within India, this is the 5th largest industry, and also accounts for 10.66% of the gross value in the agricultural sector. And this is the one sector which is always showing a double-digit growth annually in our country. And if we see the major segments in this food processing sector, we are there as number 1 or number 2 or up to this number 5, rank 5 in the world production. Total food production, we are number 2, and the fruits and vegetables, second largest dairy producer, then oil seeds, meat, marine products, any commodity if you take, we are there within that rank 5. Okay, but if we see the global share of India, in any of these areas, you see, we are the number 2 in fruits and vegetables. What is the share of our Indian products in the global market? It's very less, 1.2% in fruit, 1.6% in vegetables, though countries like Spain, USA, where they're lagging far behind us in the production aspects, but still their contribution, you can see that 11.7 and 8%. And similarly, the other commodities also, except food grains and spices. Okay, food grains, we are doing better. Like 28% our contribution is there. Spices, though we are known as the land of spices, our share in the global market is only 18%. There is a lot to improve in this sector also. And if you see the what we process in our country, like if you consider the individual states, except 1 or 2 states, all other states, the processed food industry status is only in single digits. You can see here, Tamil Nadu and Maharashtra are having 2-digit numbers, but all other states, it is less than 10 only. And where we are standing in the processed food sector, you see the developed countries like Germany, the 72% of the food items, food commodities which they are consuming, it is in the processed form. Whereas in our country, we are consuming more than 50% in the raw form only. But that means the nascent stage of food processing in our country, we need to go a lot. There is a lot potential with a lot of consumer base in our country. And where is the lacuna? Actually, most of our food processing sectors, it is in the micro food processing sector. India's micro, small and medium enterprises, it is the second largest in the world itself. And nearly 25 lakh food processing enterprises are there in the micro or small or the medium scale. And they are only contributing most of these processed foods in our country. And coming to the challenges these micro industries are facing, they don't have the modern techniques, access to the modern technologies, or they know how to brand or market their products. they are having deficiencies in the capital as well as the bank access to the credits, and most of them may not be aware about the latest technologies as well as the regulations which our country is following, what are the safety things to be followed, and also they are having the inability to interact with the supply chain also. So how we can empower our food processing sector so that by empowering our processing sector, we can increase the global market, we can make our local products globally famous, and also reduce a lot of wastage, and we can promote that waste to wealth concepts in our country, and also more value-added components in the food processing we can create. And there is always a bright future for the food industry, as we all aware that during this pandemic situation for the last 2 years also, if you take any other industries, always there was a slowdown or a growth, stagnancy was there. But except this food processing industry, still that pandemic period also, this industry was growing at a considerable rate only. So because of the spending capacity of the Indian middle class person, it is changing in their lifestyle due to rapid urbanization, more employed women, changing their family system, lifestyle system. Nobody wanted to spend more time in the kitchen. They wanted to have ready to cook, ready to eat items. So there is a bright future. And also they are telling that survey is suggesting that by 2025, the spending capacity of the Indian middle class is also going to be double. So always there is a scope. And now I will come to some of the emerging techniques. I know this is a very vast topic. I cannot cover it everything within this 15 minutes, but still some of the emerging techniques or the future foods which we are working on at our institute, NIFTM Tanjavur, I'll be focusing more on that one. And now everybody, all the consumers, 100 years back, people were taking food for energy, and 50 years back, like they were consuming it for the nutrition. And currently, these consumers are eating the food for their soul, not for either energy or nutrition. Not only for that one, they are eating it for their soul. They wanted to know from where that raw material for their food is coming, what are the technologies they are using, whether all the ethics are followed, human ethics are followed, any child labor is involved in that one, whether it is meeting out their required nutrition. All these things are combined together now. So now the people are moving towards more healthy foods, and also like a ready to cook and ready to eat form. And now this UN has announced the superfoods. Superfoods means this will give you the adequate nutrition, and also all the required vitamins, minerals, everything will be included in this one. For some of the examples are listed here. You can see here some berries, fermented products, green tea, even coconut water. And you see the last one, millets. Millets is actually, it's a very cheap source, but very potential candidate for the health requirements of our human beings. And UN has announced for the next year as the International Year of Millets. A lot of possibilities are there to exploit various value-added products from these millets also. Now our adults' interest is changing more towards this superfoods, because they will get the required nutrients, vitamins, essential amino acids, fiber, and macro and macronutrients. Everything will be included in this superfoods. And also people wanted to have customized nutrition or personalized nutrition, because my nutritional requirements will be different from my son's or my daughter's nutritional requirement, and especially it will be different from your nutritional requirement also. And we have seen in the morning in the keynote address the concept of 3D printing, how they are using it for the construction of the buildings and other works. So similarly, same technique we are trying to utilize for the food also. Food 3D printing, and even now 4D printing is also coming. So this is an idea where the customers can tackle this issue. Whatever nutritional requirements are there for the individuals, they can meet out through this 3D printing, and they can have their personalized nutritious food in whichever form they want, whatever shapes they want, they can have it through this 3D food printing. And at NIFTM Tanjavur, we have developed our own indigenous 3D food printer, and also the publications as well as the book on this 3D printing was first time released in our country from scientists from NIFTM Tanjavur only. You can see here, even chicken, you can enrich it with the fiber also. Chicken usually it won't contain fiber, but we can have through this 3D printing, somebody who likes chicken very much, but they are lacking in the fiber content. So you can enrich this chicken with the fiber content, and also a lot of waste materials you can make it or bring it into the printable form, and then you can make your required nutritional snacks or any other products. And then another area which is emerging with the vegan trend in the consumers, that is the plant-based milk as well as the meat analogs. And the market is also growing at a very fast rate for this meat analogs as well as the milk analogs. Actually, 10 years back, Beyond Meat, one company, they have already made this plant-based meat in the product form, like a burger form, combined with KFC. They have made it into the reality, and it was well received by the customers also. So those who don't want to go for this animal meat, they can go for this plant-based meat analogs. And the advantage of this plant-based meat is that it is avoiding the carbon footprinting also in the process, and lot of options are there, a lot of sources are there by which we can go for this plant-based meat analogs like oil, seeds, cereals, proteins, even legumes, pulses, and even our jackfruit is a good candidate for formulation of this plant-based meats. And another area which is getting more interest or more attraction is the entomophagy. Entomophagy is nothing but, some countries like China, Thailand and all, they are eating the insects for the required protein content and all. So now insect eating means we are having, because of some traditional approaches or because of our culture and all, most of the people will be saying, showing their reactions to this one. But the fact is that nowadays a lot of research and a lot of products are also there in the market in which the protein extracted from these various insects were incorporated. This is a good source of protein, actually, these insects, and it is also a good protein also, with bioavailability of that protein is also very good. So this is one of the emerging area where it is going on, and this is the plant-based milk and meat analogs I already mentioned. Through the 3D printing, we at NIFTAM Tanjavur also, we also have produced a meat analog. And one thing we need to consider here is the taste as well as the texture. The texture matters a lot. So the ingredients, we have to have some binders and some stabilizers which we need to add on to this material to have that proper texture as well as the taste, and also the price. Price is the major issue which is preventing the popularization of this plant-based meat in our country. And coming to the plant-based milk, this cow milk, many people are having lactose intolerance, like that means the lactose is the milk sugar which is present in cow's milk. So some people are having allergy to this sugar, so they cannot consume that milk-based products like ice creams or whatever it is. So, and as an alternative to that one, nowadays the plant-based milk is getting popularized in the market. So soya milk or coconut milk, even millet milk and other milks from the pulses, these are getting popularized. And we also have developed some of the products based on this plant milks, nothing coconut milk. We have developed the ice cream, and ice cream is a very fast moving consumer good, and it is liked by everybody, like a child to an old person. Everybody will love to have ice creams, and so we can give a healthy ice cream through this plant milks. Like in coconut milk, actually the in mother's milk there is one immune boosting component which gives that resistance or immunity to the kid. That is the lauric acid. The same component is there in our coconut milk also. So that also we can introduce into our ice cream. And apart from that, the required minerals and all the essential amino acids, even omega-3 acids also we can introduce into these ice creams through from the plant source itself. Chia is a good source for that one. Chia, already I mentioned earlier that it is a superfood. It is nothing but a small grain like a cereal only. And then millet milk is another option by which we can go for various products, not only ice cream, even the flavored milks and although this milk powder and many bakery products we can introduce through this non-dairy millet ice cream also. And the advantage is that it is having fiber as well as protein as well as all the minerals which we require. Everything is included in this millet. So that is the millet milk, or not only millet milk, all the plant milk is getting popularized nowadays. Then another area that is coming to the grain storage. I mentioned earlier that we are the #2 in the world food grain production, but you see the losses. Nearly more than 150 million tons of grains are getting lost during the storage itself. So that is more than enough to feed the 1/3 of the starving population in the world. So how to avoid this losses during the storage especially? And for that, various IoT-based techniques are developed at our institute in collaboration with various organizations like FCI and some UK collaboratives, like some industries. So one such technology is the smart warehouses. Actually, the idea is that when the grains come to the godown itself, there, while passing through the conveyor, an inline moisture meter will be there based on the infrared. It will analyze the moisture, and if the moisture content of the grain is more than the safe storage limit, then automatically it will be diverted to our radio frequency sterilizer. Here, not only drying, but sterilization of the grains also will be happening. That means that whatever insects or egg or larvae, anything is there in that lot, that also will get disinfested, and then it will go to the storage godowns. In such a way, we can reduce a lot of losses which is happening due to the excess moisture present. This excess moisture create a lot of insects as well as a lot of spoilage in the grains. And another approach is the sensors. Biosensors, and this is one sensor which we have developed in collaboration with the UK industry as well as institute. And these sensors, we have deployed now nearly 100 sensors at various godowns of FCI in our country. And the advantage is that through these sensors, we can get the temperature as well as the relative humidity of the grain stored at different places in our country through the cloud computing. That is the IoT based technique. So here the godown operator can get the details in his mobile itself, and accordingly he can take the precaution measures where either aeration is needed or heating is needed. Like that, he can take the precautions also to avoid the losses. And another technique is that, you know, now most of the godowns, they are using this aluminum phosphide or bromine for fumigation purpose. But our insects are now resistant to these chemicals, and some of the chemicals even banned in other countries we are using. So to avoid that one, what we are doing now, some botanicals or some extracts of some plants, and also ozone fumigation is a emerging technique where there is no residue, chemical residue like this, and we can prevent the insect infestation in our grains. This is some of the emerging techniques which we are following for the grain storage. And then coming to the recent regulations released by our FSSAI, they are advocating for the low salt, low sugar, and low fat foods. Okay, so in this sense, we at NIFTM Tanjavur, we have developed a nano salt. This salt, the advantage is that by consuming even 40 to 50% lesser salt itself, we will be getting the same perception with our normal salt. So that much salt intake we can reduce. This is the effect of the nanotechnology. By reducing the size, we can enhance the surface area. So the more that filling will be more there. And also low sugar or the alternative sugars to our normal sugar. And now the global perspective is that they are charging more taxes if the sugar content in the food is high. Similarly, the fat content also, because it is leading to various disorders like heart problems, and also they are advocating for the low fat also. So alternate fat as well as alternate sugar technologies, that is one of the emerging area, alternative food ingredients by which we can reduce this risk for the human life. And also we can analyze like the whatever commodity we are consuming, how it is going to get digested in our body. For that, there is an artificial digestion system which will mimic the human digestion system, and this is Asia's first system which is available. Here, oral tribology, how when you consume the food, how it will get masticated in the food, and from there till it absorbs in the small intestine, and after that residual part rejected through the large intestine. till those portions we can analyze it, and we can also find out the glycemic index of individual foods, and many industries are sending the samples for this analysis also here. So by this we need not go for the human trials. Human trials we can mimic here, and we have validated this system with the human trials also, and it was showing close proximity, nearly 98% close proximity with the human trials also. So another concept which our previous speaker was also telling about the waste utilization or converting the waste to wealth. So most of the food industries are also working in this angle now, that is the zero waste technique or the waste to wealth concept. We also worked with this aspect, and we have developed one product along with the PepsiCo. You can see these crisp chips. This is actually made from the waste products only. So these are the waste items we have utilized here. Mainly the base material utilized here is the potato starch, which we extracted from the peel as well as the fines of the potato, which they were getting from this potato chip making industry. And also here we have fortified the items with the fruit industry waste, like pomades from the grapes as well as the pomegranate and the oat and apple pomades waste, and then pulse industry waste also. This is a very good source for the protein. Okay, so this we combine together so that instead of wasting that materials, we can utilize it and convert it into a good product, a very healthy product with a very reasonable price. And another thing is the jackfruit, which you are all familiar with that one. And we know that only 30% of this jackfruit is in the consumable form, and remaining things we are wasting. Like 70% is going as the waste. So we can convert this waste also as a because this waste contains lot of fiber in it, and converting that into fiber as well as some other bioactive materials are also there. We converted that one into biodegradable plates, even edible plates and edible cones for this ice cream also. So like that, this is actually coming under the sustainable development goals of the UN also, like resource recovery and zero waste concept. Okay, so and another emerging trend, which now food processing industries are looking, is the non-thermal techniques for the sterilization or pasteurization aspect. Usually they will be using thermal techniques. The disadvantage of this thermal processing techniques like retort processing or sterilization or any heat treatment, most of these bioactives or the vitamins or the nutrients, they are heat liable things. So they will get damaged due to this heating process. So to avoid this one, now people are going towards the non-thermal techniques like high pressure processing, cold plasma, pulsed electric field, ultrasonication, ozone. I already mentioned for storage application of this ozone also for the sterilization purpose, and supercritical fluid extraction. Like that, many non-thermal techniques are now emerging so that there won't be any heat application. So you can preserve the nutrients as such, and also maintain the fresh like taste. You know, like coconut water and tender coconut water, it is a most lovely product, but once you go for exposing it to the environment, it will get deteriorate immediately. So if we go for any thermal treatment, that natural taste of coconut water is getting lost. So how we can preserve that one? HPP is a very good candidate by which we can preserve that fresh like all these non-thermal techniques are having a lot of potential, and in abroad countries they are utilizing this one. In India, some few companies, very few companies only started using this technique. So this is one emerging technique. And another one area is the virtual marketing and also the sensory analysis things. Virtual marketing, actually through this virtual reality, the consumers can experience the actual marketing, and also through the eye tracking mechanism, we can even analyze the consumers will be attracted towards which type of product, and where what color is attracted by the consumers, and what is the level of that perception by the consumers. All these things we can analyze using the data mining techniques, using the support of the softwares, and by which we can go for better design of the packaging material or better placement of your product in the supermarkets. All these can be made easier by this virtual marketing. And also coming to the sensory aspect of it, now we can mimic our taste as well as the flavor by our tongue as well as our nose, which will be mimicked by the e-nose and e-tongue technique. these products can be tested easily within no time, and they can be tested authentically. And also now softwares are available. Even the facial expression of the sensory panel also can be captured by the softwares, so that based on their facial expression, we can judge whether they liked that product or what is the perception they are having. So all these are the emerging trends in the sensory aspects also. And then coming to the drying techniques, drying is the age-old preservation methodology which people are following, drying and dehydration. And now there are many modern techniques like spray freeze drying combination, because freeze drying is the most suitable one to preserve the quality. But freeze drying, it is a very costly one. So how we can get a better quality or on par quality with the freeze drying by using other techniques. So here comes the conductive hydro drying, or we can also call it as the refractive window drying, and also low temperature, low humidity drying. Like different drying techniques are now emerging, so as to get the equal quality like that of freeze drying with a lesser cost. So these are some of the emerging techniques, novel drying techniques which we can use for the drying of heat sensitive ingredients like probiotics and all. And also the electromagnetic spectrum, you are well versed with all these spectrum like X-rays, UV, infrared, microwave and all. So these are also having a very vast application in the food processing sector, like X-rays and all we can use for the non-destructive quality evaluation. Like human X-rays we are taking to detect the internal defects. Same thing we can use for this soft X-rays we can use for our food commodities also, to judge whether there is any internal damage before we send it for or packaging or export purpose, or before we send it to the market. We can have this system. Similarly, like acoustic systems are there, machine vision systems are there. So without destroying the sample, we can analyze the internal quality as well as the external quality, and we can sort it grade A, grade B like that, and then we can send it to the consumers. And another technique is the UV. UV is also nowadays using for the disinfestation purpose, and infrared there is having a lot of applications, microwave also, and radio frequency waves are also using nowadays for sterilization purpose, because this is also a volumetric heating without generating much heat. Within less time we can heat the materials, same time we can have this sterilization effect also in the radio frequency. And nanotechnology is another area which is having lot of applications in the food processing, like nano emulsions, and already I told about the nano salt which is giving the same perception with less quantity. Similarly, we can have the nano nutraceutical delivery system by the nano encapsulation, like some certain bioactives which should get delivered to the particular position in our digestion system, is that also possible by this nano encapsulation as well as the micro encapsulation techniques. And also in packaging there are a lot of applications for this nanotechnology as well as the nano materials. And then coming to the packaging side, like nowadays these plastics are banned by our government, so we have to go for various alternatives for the single-use plastics. And there are a lot of potential applications, that is the packaging material from this bio waste. Like onion is a very good potential candidate, like bagasse, this sugarcane industry, they are getting that waste material. Then rice, straw, wheat, paddy straw, like lot of biomaterials which is getting wasted during the processing of certain raw materials, that we can convert it as bioplastics, or even for edible coating of the fruit or vegetable. And also we can make some trays for packing the biscuits, and also we can have some secondary packaging material, secondary or tertiary packaging material, some wrapping within some biscuit packs or cake packs, and outer there will be another one more packing. Like that, lot of packaging applications are also there. And then this is like a active and intelligent packaging system. This is an emerging trend in the packaging. Like you can have some indicators which will tell you whether the freshness of your product is lost or not. This is one indicator developed. The color will change from green to yellow, then orange, and finally to red when it is completely spoiled by the microbes. And similarly here, another spoilage indicators for the tomato. This is one chip you can insert into your packaging like that bag of tomatoes itself, and it will tell you, because during transportation and all, this system we can use, like when the tomatoes are spoiled, they will indicate even the truck driver or that worker in the cold storage unit, he will get the alarm that this tomato is spoiled, so you cannot use it, like that they will get the alarm. So that type of intelligent packaging and active packaging is also there. And then another thing is that bio material we can use for the biodegradable packing, like even plates and also edible cups, edible plates, like what I mentioned earlier from the jackfruit. So similarly, so many techniques are now emerging to convert bio waste usable form or a value added form, so as there won't be any waste or zero waste concept, and to enhance the income of the producers also. Like we have developed from the onion this packaging films and carton boxes also we have developed from the onion waste, so which is giving an additional income to the farmers also. So we can invest smartly towards a healthy world and towards a hunger-free world. And our vision is through food processing, we can make our country the food factory of the world, because we are having lot of resources, but only thing is that we need to process it properly. We have to tap the potential. In Kerala also, lot of resources are available. I my humble request to the Professor Sudhir and the team to encourage more processing industries in our state, Kerala state, because we need to tap a lot of potential from Kerala. And thank you so much for giving me this opportunity. I don't know, I was rushing because already the time is running short. So thank you very much. If any questions, you can just have quickly 1 or 2 questions.
Thank you so much, ma'am. Thanking so much for giving us a detailed outlook on the different technologies and approaches in the food processing sector, and also for detailing the technologies available at NIFTEM Tanjavur. Thank you so much. Great to see a lot of possibilities available in this sector. Thank you so much. I will move to the next presentation. Next presentation is speaker is Professor Alex James, who works in broad areas of neuromembrantic systems, intelligent semiconductor materials and memory devices, moves electronics, neuromorphic processors, analog and mixed signal circuits, and imaging systems. He received his PhD degree from Queensland Micro and Nanotechnology Centre, Griffith University, Australia. He is currently the chair of School of Electronic Systems and Automation at Digital University of Kerala. He is professor in charge of Maker Village that supports over 80 plus hardware startups. He is the chief investigator of the Center for Intelligent IoT Sensors and India Innovation Center for Graphene, both centers performing translational research and developing new products to the market in collaboration with the industry. And with indeed my pleasure to invite Dr. Professor Alex James to the invited talk. Sir, please.
Okay, thank you. Let me share the presentation.
Yes.
Is it visible? Is it visible? Okay, okay. So I'll given it's like I'm coming in between lunch and I'll try to keep it brief. I'll not make it too technical, but like touch upon some ideas. And if there is like any detailed discussion required, I'm happy to take it like offline or even if time permits, like we can. So I'll start with like the idea of like Industry 4.0, and if you might have heard this term Industry 4.0 quite a lot, and today people talk about Industry 5.0 as well. So in all this, one thing that you would see is you see computation as one of the most important aspect, whether you do automation, big data, cloud computing, building like autonomous systems with robotics, using IoT, or even having data management. At the core of it, you need memory and you need like computing. And that is the only underlying truth that is physical there. Rest of them you can always come up with various architectures, but building those is has been one of the biggest challenges in the last several decades. So if you look at the Moore's law is basically what defined the scaling of transistors. And over the years, every year we have tried to push the boundaries of the technologies, the size of the device, what we can go through. And today you see a huge amount of transistors put in the same amount of area. Where at one point in time we only had like 1,000 transistors. Now we are looking at in billions of transistors. What it has done is it has pushed the boundaries of computing on one side, and it has also changed the way in which we build devices. The way we understand how computing can happen has also changed because of this. Just to look at what it has done. In fact, looking at the evolution of the big data itself, big data has been around for quite a bit of time, early from 1980s, but it has never been at that scale and use till 2000. And if you look at the transistor technology, what was there around that time, you're looking at 90 nanometer in 2003. And by 2014, this was 14 nanometer node size, what we were looking at. And during that time, the computing architectures also scaled quite a bit. And you could pack more of memory, RAMs, more of computing into the servers that were built. And this basically democratized many of the technologies that we see today. And in fact, it paved way to rapid growth in a large number of fields, whether it's basic sciences to whether it's engineering disciplines. Most of them required that computing to push that growth. And this is what it has done. And if you look at the studies, number of studies in AI, that's a very clear example of the jump that has happened because of this computing, and how having those kind of computing resources really push the research as well. Today, people can experiment any neural network, writing 4 lines of code. So I usually see those programmers as the happy people, jumping, dancing. They're the easiest. They don't have to worry about anything that is difficult. It's the easiest part. And then you have the hardware at the bottom, where all the pain actually comes down to. Because if you want to enable and move from say 7 nanometer to 5 nanometer, what is currently done is 5 nanometer, and people are pushing towards 3 nanometer in the industry. This is not easy. There is a lot of know-how that goes into process engineering, that goes into kind of equipments that you build to make it happen. You also need kind of new devices to work with. Have to come up with various architectures that can be built on top of it, and so on and so forth. So the list is quite endless what you can do there. So what has been the problem? Scaling, if scaling was great, what was the issue? Because if you can just reduce the transistor size, that was perfect, and we were able to reduce the transistor size. But when it comes to microprocessors, you would see the frequency got limited. You cannot push it beyond a particular frequency. Power has been a huge problem. And in fact, if you look at almost all the architectures that are today that is trying to push the boundaries of computing, you would see that the CMOS technologies more or less come to the limits of energy per computation. So if you want to push further down, make the devices low power, when you pack more and more devices, if each device consumes the same amount of power, you're looking at overall the chip to have much larger power, which you don't want. So that's where like new devices, materials, and architecture comes into picture to a great extent. If you want to find like practical use. And whenever a new device or material is introduced, this is not an easy process. Taking it from the concept to actually like taking it to industry, it would take usually like it used to take like over 3 decades or 4 decades or more to like some of the technologies like recently like people have tried. It still took like almost a decade to push it to even like a small portion in the industry. So semiconductor industry as such, like they are very much like what you call like dominated by CMOS. So anything if you want to like replace CMOS, that is seen very in a very skeptical eye, because that requires like huge amount of investment. So whatever new devices that you want to introduce, like you need to really like see whether the practical side of things, like how you can integrate that into the current process, and that's not an easy job either. So people have been like looking at like, okay, scaling, and you can see in the y-axis the scaling part that has happened, and this has really pushed the digital processing, information processing part of it. And more than more, basically you try to achieve like for a same node technology, achieve much more than what is typically achieved with a digital system on chip kind of solution. So for that, like diversification is seen as one of the things where you introduce like analog, passive, biochips, like and so on and so forth. Also looking at like various integration technologies, packaging technologies. 3D integration is one of the main thing that is looked at. Try to like put more and more things onto the same chip area. Maybe increase the volume, but like area remains like more or less same. So in that way, more can be done, and people have been like in industry, like people have been trying to push the boundaries. In fact, like this is one area where you would see the amount of know-how which is there in each one of those foundries or each one of the design labs are probably like going to be like a lot more than what is available in the public domain. And that's why if you're working in like semiconductors, or if you're working in areas of this nature, like it's important to talk to the industry quite a bit, because many of the things requires like to implement, it requires like huge amount of funds. Usually research labs will not be able to afford many of those things. And if you look at like the future of computing as such, like this is a very nice way to explain, like we lose group, like he had like a very simplistic way to explain this. Like you have all these CPU, GPU, and CMOS based technology, all of them having like various like boundaries now evolved. Basically, you have heat wall, the temperature, power dissipation, and all those things being a huge problem. Then you have the memory wall, where you have the memory bottleneck, coming data rates and all those things. The speed being a problem. And then you have the limits of the Moore's law, practical, like, cost increasing quite a bit. If you try to scale it up, with the CMOS, it's practically almost like, seeing to be impossible to maintain that kind of costing. So people have kind of moved to many other kind of devices. You can see FinFETs and others being used, but anything more than that, like it's still like quite a long way to go. Whenever people say like a fascinating device, like which would like change the world, you need to always take it with a pinch of salt, because it's simply like they are not like industry ready, and it will take like several years and billions of dollars of investment to reach there. So alternative to that, like there are like architecture based like things that you can think about, like the kind of like different computing architectures, which is seen as like more promising way to approach this and remove many of the issues that are coming with like Moore's law and the memory wall and the heat wall that we are typically like faced with. So thinking more towards like cognitive aspects, we are looking at intelligent computing being like one of the key areas. Big data and Internet of Things, these are going to remain there, and for next 10 years, 15 years, 20 years, like almost every other field of science, branch of like engineering would be using any of these things. But most of the people who are end users, they may not be too much worried about like how the things happen inside. They would be looking at like, is it like running effectively? Is my device like reliable? Like, is it, can it do like those computations effectively at like short period of time? Is it like cost effective? Can I buy it like at extremely low cost and so on? So areas for better memory related like processing in memory computing is very promising. There are a lot of like applications. There are a lot of practical like implementations shown on in memory computation, which has shown to work much better than like many other processor von Neumann kind of architectures. Then we have neuromorphic computing, which is trying to like address. Today, neuromorphic computing is a bit more broad than where it started from. Like when it started, it was more into biological neural networks, but today, like neuromorphic computing is a bit more broad. So we are looking at like artificial networks as well as like we're looking at biological networks to be modeled. And then we have like better intelligent sensing, where you try to integrate like various processing onto the sensors, and or close to the sensor, which people call as like edge AI computing and other things. Now, when you do like edge AI computing, again, like the power factor when you use a traditional microprocessor, this may be very, very high, and you would need like batteries and you need like power as being like one of the critical aspect how to deal with all those things. But at the same time, if you are using like alternative like an architecture ASICs and other things, you could like achieve like much better performance. But obviously, like when you do that, it's not that user friendly. That someone would need to know how to build those things to make it work. So democratization of that is yet to happen. Like to have like dedicated low power chips, which like anyone can just put and use. That is still an ongoing thing. So all those areas are like quite promising, and we can see it as alternative to the existing way of doing computation. And this can go into like from edge devices to like servers to any computing need that we're looking at. And if you look at like the areas like where intelligent systems like kind of like are putting in like a lot of weight from quantum computing, where you look at like qubit based like computation. So some of those highly parallel computations that we would want to do, from cryptography to image processing to video processing to all those things. If the qubit errors that we currently have in the quantum systems that are there, like that can be reduced, then this becomes very promising. There is active research going in that direction. There is a whole field of quantum AI that is being like developed. There is molecular electronics looking into like various kind of like organic molecules, molecular spintronics and other things. Then there is spintronic, which is seen as an alternative way to build like devices. You can achieve like a lot of scalability with that. But the problem with those devices as of now is that like many of those promising lab devices are not really that promising when it comes to like large scale fabrication. So there is still like a long way to go in that. But there are like one or two like good devices which have been adopted like in memories and other things. Then there is a whole range of 2D materials, like starting from graphene and many different like 2D materials, like last 2-3 years, like people have found application in, and they can be moved into devices as well to build like various kind of devices, like memories and other things. And then, but again, like those things are at still like an early stage, and it will take a lot of time before it will be fully adopted in industry. And this is something that we need to be very aware of. But there may be some practical applications like photo diodes and other things where it can be straight away used. But I'm specifically talking about computing, and in that sense, like the logic devices, this may be a bit far way long to go. the extent and beyond CMOS, currently, like, people are looking at like various ways of like integration in the in industry to actually push those boundaries in a very practical way. So if you take like a very different route, I mean, it's good for research, but then eventually, like when we talk about beyond CMOS, those technologies and methods should be compatible to those things that you can produce at scale. And neuromorphic is again a very practical way, like you can use the current devices, create like various architectures to build like analog or digital like systems, which is not necessarily doing a monument-based computing, but it's more like you have in-memory computing and all those things coming into picture there, creating like the kind of neural networks that are used today by the programmers, the machine ML guys, or the traditional AI guys, like deep learning and other things coming in. This becomes like kind of like a very promising area. So I put those yellow ones like where we are working like very actively, and we are building like things around that. So when it comes to intelligent materials, the word intelligence has got a very specific meaning. So when we talk about intelligence, it's not like cognition itself. It's also like being aware about the environment and being able to adapt to the changes to the environment. And when people talk about intelligent 2D materials, it's exactly what it means, like the materials that can adapt to the environment, materials that respond to particular stimuli, where you can find some applications for it, like in self-healing mobile phone screens, shape-shifting airplane wings, or targeted drug delivery. And this application was shown by Novoslav, like and his team, where they use like MOS2 Graphene to like show like how you can work with like drug delivery systems. We have a couple of centers, like briefly, like they're all working on like translation research. Like what we try to do is like we are taking like some of those ideas and translate it into like a real product, and we work with companies for doing that. More details, like if someone wants, like I'm happy to share. But essentially, the idea there is like people come with like a proven like research, and those research ideas, like we try to see if it is possible to convert into a real product, working with various companies. And a couple of centers, like one on graphene and other on like IoT sensors, where we are looking at mostly the hardware side of things and building systems out of that. So there is like test facilities and manufacturing facilities and other things that are being built, and also some incubation related facilities that are being like developed. Our focus mostly is on the product engineering and looking at like mostly towards like how to make it reliable and realistic. So coming back to the intelligence part, like how to one way of building that, like in memory computing, and how you can use like a 2D material in something like in memory computing is by building like memories out of it. So there is like lateral structures or vertical structure, heterojunction structures that you can build, where these can be like in your memories, like a resistive memory. And the way in which like the kind of material you use, like you get like different properties in terms of like conductivity, the endurance of the device vary, and the variability of the device, like they also like change from one device to another. And in many cases, like when you want to take this to like a real what do you call, like a scalable situation, the thing would be like you don't want to have like the complete like a new fab to be set up just for this. So you want to see which ones of this will be like much more like reliable to be scaled or put on top of whatever process that is. So you can build like with memories, like you can build like simple neural networks using weighted summation, and these memories itself or memory stress itself can be built with like various different structures, from the 2D based like materials to like traditionally oxide based like materials that are there, which are very commonly used for this. And we have been like building various kind of like networks. Actually, we reported like some of the first like analog neural nets, like with like chemistry systems built, whether it's HTM, whether it's like LSTM, all those things, like several chips were built in the past, and many of them have been put into use in some of the practical things. Like for example, one of the work that we did was like put that into a toy, where like the toy would respond to the speech of the kid. So those kind of things you can quickly do. You don't need like huge power for that. You need to keep the power very low, and for that, like and different architectures have different like what you call like application processing speeds, like all sort of things. So when it comes to developing, converting that to product, it has to be very specific. So you basically like you're trying to achieve that particular power levels, that amount of like voltage requirement, like energy distribution. The power distribution becomes kind of like a very critical thing within the chip. The speed at which like you want to distribute, the amount of data that you want to use, all those things becomes like much more critical and resource constrained if you want to make that like very effective system. So from generating networks to HTMs to there was like one work on like how we can build like using an AI chip to build an AI chip. So that was also like another thing. We are currently having like an AI chip center. Like, we work closely with like some of the foundries to build few of the AI cores. One based on like basically RISC-V, and the other based on ARM. So there are several series of processes being built, and we are trying to put it onto various applications. So some of them are like accelerators, some of them are like reconfigurable systems, which can be used. Trying to look at like security chips and other things. Like a few of them are in already gone into fab. So possibly in like few months, like we'll have the actual testing of all those things. There have been like few works in the past, like where we have been we have actually like built like image sensors, real-time image sensors, where we have put in like some kind of like analog intelligence into it, and not digital, purely like analog. Then we have looking at like crossbar resolution, like super resolution for those memories. Then a ML coprocessor, which can do like few set of like machine learning algorithms in accelerated way. We have been collaborating with many universities for various things, because some of the technologies like are a bit tricky, and we have to test it on some facilities. You don't get like all facilities around, so you got to see where the best things are, and then try to work. And some of the other practical applications that we have like deployed, like for example, high voltage insulator like monitoring. We had like done some work on that, like adding intelligence to the drone, making it like be able to detect like insulators, high voltage insulators, detecting the defects and all those things. And what was inside the drone was like these kind of processors which could like do the high speed, like this thing, detections, classifications, and all those things. Then we are currently working on various kind of drone networks, where you're looking at like various kind of security related things related to drone networks, and we're building our own hardware for it, like from scratch, and we're using like some of the what you call like existing like architectures, but like using our own chips. Then wireless charging is another aspect, like where we need like a lot of optimization to be done, and for those optimization, again, we are using like our own accelerators and other things, and we are trying to see like how to make it like more effective, cost effective, and a few of them are working on that. Autonomous driving is another area that we are looking at. We're collaborating with some of the industries on this, and there is also like consumer electronics. Like we have like few companies that we are working on, like improving some of their existing products, and we are possibly like you'll have few versions of what you call like refrigerators and washing machines coming out with like what we have contributed. And then there is many different AI accelerators. As I showed like briefly, like we are building various accelerators. We are planning for a few complex chips over the next 2-3 years, and see where we can push that, because our problem has been like one of the things which with increasing the complexity is the computational requirement. It goes like crazy. So many of the things like we'll have to run it like outside, like in some of the cloud facilities, simply because they consume very large amount of like data and processing. But anyway, like as of now it is okay, but I'm thinking like in a year or two this will be a huge problem. Because as and when we scale it, like our present designs itself, like some of them takes a lot of time to see. We are setting up like few of the things like to physical facilities, like PCB fabrication and the class 100 clean rooms and all those things are being like set up. Hopefully those things will help. And we already have some PCB facilities and all the VLSI related like design labs are all there. So if anyone wants to collaborate, like, we're happy to do it. So just to give some final thoughts on this. So one of the biggest challenge, like we are talking about semiconductor revolution in India, and there are a few major things that we need to consider as going ahead. Because many of the equipment manufacturers, like what we have today in the world, like they are all outside India. So if you want to like set up like a fab, it will take at least like a year to build the equipment. And specifically 1 or 2 countries are the only ones like who create like some of those equipments. So unless and until like we don't make our own equipments, like this is going to be a problem in the longer run. Another thing that there is a huge shortage of people who know like chip design properly. Although there are many people who graduate in electronics, a large majority of those people probably end up taking up like software jobs and other things. And which over the years, what it has done is today, if you want to find someone who can do chip verification, you don't find people. And there is a huge shortage of that. And this has again like led way into academia as well, that finding like good people in academia who has like practical experience in this area, they're also quite limited. Like the large scale integration related experience, that is kind of being a challenge. Then there is like test and packaging facility. This is going to be a major issue as we look ahead. Because as and when we increase like the local production in terms of like sensors, in terms of like the chips, you're looking at the need to have like various different kind of packaging facilities and also testing facilities. And that growth can be quite fast. So there needs to be some preparation for that. And there is like the high-end computing infrastructure that is required. So just by rough calculation, if we go into this, we need at least, if you want to do full chip simulations and all those things, we are growing in a revolution kind of thing. Like, we are looking at every 100 kilometers needing to have like some servers. And you can draw parallel with what US has. We are per capita wise like very low in terms of like computing power. And US is one of the places like that's leading in like semiconductors. So if you want to have a competition of some form in the long run, that server computing space is going to be very important. And the last part is like the challenge that we have with startups. Many of the startups like when the last 2 years, what has happened is like getting chips has been difficult, getting sensors has been difficult. Even if you get like the sensors, it's or like the components, it's at a very high cost than what it actually cost. So there has to be some way to incentivize, irrespective of like irrespective of whatever is the cost. Simply because if you don't do that, like many of the ideas will not get translated to real products. it will be good on paper, but like it will not translate. Because that kind of incentivization is required to really push the growth of manufacturing at a local level. So these are just acknowledgements. Some of the people like who have been like working on many of those things that I've shown. So then we will start going at this stage. Thank you.
Thank you so much, sir, for enlightening us with the advancements in electronics, digital technology, and in computing. Thank you so much, sir.
Thank you.
And now we have Professor K. Satish Kumar, who is the Professor and Head of Department of Future Studies, University of Kerala, Thiruvananthapuram. After completing BSc and MSc in Mathematics, he pursued doctoral studies from CSIR, National Institute for Interdisciplinary Science and Technology, Trivandrum, on the studies on chaotic rheological parameters of periodically forced suspensions of weak Brownian slender bodies in simple shear flow. His areas of interest include modeling and simulation in areas such as suspension rheology, polymer rheology, and dynamics, biophysics, geophysics, and expertise includes Brownian dynamic simulation, supercomputing, parallel programming, nonlinear time series analysis, wavelet analysis, social network analysis, wind modeling and forecasting, and citation network analysis. He's a member, Board of Studies of Future Studies, University of Kerala, and member, Academic Council of University of Kerala. It's my pleasure to invite Professor Satish Kumar for the invited talk. Over to you, sir.
Thank you for your kind introduction. Let me share the screen. Is it visible now? And am I audible?
Yes, please continue.
Good afternoon. In my talk, I will restrict to 15 minutes if possible because it's already too late. So what I'm trying to talk today is about automated knowledge discovery. Like, knowledge discovery, generally, when we talk about knowledge discovery, it is like data mining. You get some information or at least actionable information from the data. So that is the conventional way of looking at knowledge discovery. But now, by the invent of artificial intelligence and usually humans are finding scientific discoveries now. Whether the computer or a machine can do some kind of scientific discovery. So that by the advent of this artificial, that is at least conceivable. Some work has already been gone into this direction. So I'll in this talk I'll talk about this and just to give an overview, like where is it's going, like just basic. Even in the 60s, like the programs called Dendral. In Dendral, actually, it's a program, and it tries to give the molecular structure from the spectrometry data. Right? If you feed the data, it will come up with the molecular structure. That was way back in 1960s. Like it's more like an expert system. We cannot say that it is more of like artificial scientific discovery or anything. Then in 1976, a program called A Mathematician came up over that. And this is with the simple Lisp program. They tried to rediscover the mathematical theorems and concepts like that. Say, for example, in mathematics, if you have one research paper saying that A implies B, and some other paper says that B implies C. So you can put together and form a new knowledge like A implies C or something like that, based on first order logic. Like this was simple, but it had a lot of drawbacks and limitations. Then UNESCO came and it was trying to what you call cover up the limitations by adding its own creative rules and try to different domains. They applied this program not only to mathematics but also in the other domains. Then came like in 1984. So millions of pieces of knowledge comprise of human kind of common sense. Like it's like more than what a computer can do. They are trying to put into some kind of common sense into this. This was the what you call premise and which the knowledge discovery started. Like there's a bit old. Now a lot of changes have been happened in this area. Like compared to this stage, lot has been changed. I'll tell you some of those things. recently knowledge discovery means like there are two ways, two approaches followed by in this domain, like to find knowledge or discovery from the existing knowledge. One good thing recently, one good thing nowadays is that earlier we used to publish papers, all published papers are in the paper form. Now everything is in computer readable form, like portable document format or PDF files or something. That is the knowledge, whatever we publish, everything is in computer readable form. Then the question is whether a computer program can read all these documents and come up with a new knowledge. Even before that, even in 20s, actually, somebody has manually did that. In one paper, they say that there is a particular chemical in the plant, actually. In another research paper, sometime later published, this chemical can be used as a drug in some other disease, for some disease. So put together this, we can say that that plant is useful for this disease, right? So this kind of experiments and efforts were being carried out even sometime back. Now, because of the computational power and better artificial intelligence algorithm, now we can do better. So my idea here in this talk is to give an overall picture about what is knowledge graph and how knowledge graph can be used to find new knowledge. That is just about. There are two ways. One is called the knowledge graph, and the other method is called the word to vector. And even in a recent paper, I mean, they say some knowledge is common to all domains. Like there is in mathematics, there is a theory called the category theory, which says in one domain, if there is a knowledge, a similar knowledge may be there in another domain also. Here, this is an example. In electrical engineering, we all know about Ohm's law, where voltage is equal to current into resistance. But recently, this result, the similar result in mechanical engineering was obtained using a computer program. They say for trusses, displacement is equal to force into compliance. So this was not identified by a human being, it was identified by a software, like recent publication. So many results it has in one domain, maybe similar result maybe there in other domain. Actually, they were trying to find out that like the whole knowledge gaps and trying to fit with equations. Even otherwise, when the periodic table was first invented, so there were gaps actually. They did not know that what molecule will go into that particular cell. So, but still, they could anticipate that there would be a chemical molecule to fit in a particular cell, So this is something like that actually. Well, now let us look at what is a knowledge graph. What's a graph basically? A graph is a discrete mathematical object in which there are two entities. One is called a node. This kind of circles, these are called nodes, or mathematicians call it as vertices, socialists call it as actors. Then they are related by edges or arrows, So it has got two entities, nodes as well as edges. So that is a graph. Now a knowledge graph has got some more attributes. Suppose there is a sentence like Rama is writing a letter. How can you convert that into graph? So Rama is a subject, it's a noun, so that can be put as a node, and there is a predicate, then the letter, that can be another node. So this is being connected by the verb, right? So we'll usually use the root form of the verb for putting it. So it involves kind of natural language processing. So when you with all the tools of natural language processing, you can convert sentences into a mathematical object called a graph, or with the attributes in the edges. So what if we can convert the whole literature in one particular domain into a knowledge graph? It is like kind of a database. From you can query questions, you can get new information, kind of stuff you can get. I mean, whether there are a lot of results already published in this, especially in material science. See, for example, if you want to have a material of a particular property, how do you do that? Usually, experimental science, they go to the laboratory and experiment with that molecule, whether to get that. But how many candidate molecules, how many candidate chemicals are there? It's millions of materials are there, or chemicals are there, especially in organic molecules. So which one is the most suitable one? It may be very costly, time consuming to do experiment with all these molecules. At least you can get an idea or select some few candidate materials for doing experiment. This kind of information you can get from this knowledge graph actually. So knowledge graph is something like this. There is a text that we can convert into knowledge. Say University Kerala is located in Trivandrum, and is the district of Trivandrum district is the capital of Kerala, which is a part of India. Like if you have a passage like this, that you can convert this into a knowledge graph. At the moment, there are knowledge graphs. This was introduced by Google, and they have a pre-trained model called SPACY, or some people pronounce it as SPACY. Okay, so these pre-trained models are there, but the problem is that this is trained with internet data, like text. Common people using that kind of text may not be that suitable for scientific purpose, because we in scientific field, we have particular terminology. The language might be slightly different and may not be suitable, but this has been tried actually. This one. So the question is, if you have a lot of papers like this, all these papers, they are computer readable form, like like a PDF files. So if you look at all the literature in one particular domain, from these domains, from the all the articles, whether you can convert that into a knowledge graph, a graph. If you can convert that into a knowledge graph, you may have one piece of information or a knowledge somewhere here in this paper. Maybe that can be have a relating knowledge somewhere around here. You can put together, piece together, stitch together to get a new knowledge. That is the way using a knowledge graph actually. So essentially, by using knowledge graph, how do you find the knowledge discovery? From the published papers, you make a knowledge graph. From the knowledge graph, put the right questions or extract information and to get new information. That is possible. Now people are doing it. I will give you one or two examples, not much. Okay. So knowledge has been popular, and there are a lot of knowledge graphs already available actually. One is called Yago. Yago was developed by Max Planck Institute by using the Wikipedia information. So complete Wikipedia information they put into a knowledge graph format, that's called Yago. So you can query, it is available. You can put a query into Yago. So from the Wikipedia, all the information that is there in the Wikipedia, it is in the knowledge graph format. So you can put query and you can extract information from that actually. Then similar to that, like a BBpedia is cross-language project actually. It isn't restricted to one particular language, even with the different languages you can use. Then there is something called the WordNet. It is a lexical database for the English language, which you can use for making new knowledge graph. Then Freebase is the large collaborative knowledge basing data comprised of many community members, like so it's kind of free knowledge. Then never-ending language learning system is a semantic machine learning system that runs 24 hours a day and learning to get information from the web. So more and more information it is getting actually. So I mean, there are a lot of knowledge graphs, but still for the scientific purpose, this knowledge graph is not very developed actually. Suppose there is no already available knowledge graph or methodology or program so that you can directly use for your domain. It's not that, but there are attempts. I mean, this is a very recent publication. They talk about a scientific knowledge graph, a program called the Sci-K graph, actually, knowledge graph. So this is available. It's a publicly available code. The code is available. They are trying to make a program for scientific purposes actually, because scientific purpose, the knowledge you represent will have a different, especially because of the terminology, scientific terminology, and the common the model which is being trained with the usual test or web data from the web may not be that much suitable for this actually. And this has effectively been used in chemistry. And this is a particular paper, is very interesting one. They have come up with a program like, suppose you want to produce a product from a chemical reaction, and this chemical reaction is already known actually. That might be costly or time consuming to do that, but this program will come up with a new chemical reaction, new reaction altogether, like in a different way you can synthesize the same product. That too, it may not take that much cost or time or anything. The alternative chemical rules are formed from this knowledge graph actually. So that has been used. This can reduce the production cost and all. It is effectively been used using knowledge graph. And domain knowledge graph-based representation, and still they report that there are a lot of gaps in the domain knowledge graph construction actually. I mean, it's not a fully developed area, like whether we can construct a knowledge graph from the test. That is one area. The next concept is word to vector. I mean, I said knowledge discovery nowadays are based on two different streams, like the methodology, the route they follow is two. One is called the knowledge graph, which I have explained. Next one is the word to vector. word to vector. Words can be converted into numerical numbers or a vector of numbers. So the advantage is that when you have numbers, you can add or subtract or multiply. All the arithmetic operations are possible with the numbers, but with the word that may not be possible. So they are trying to convert the words into numbers, like vectors. Like, one way of doing it is you consider the same sentence like Rama is writing a letter. We can put this into a neural network actually. So we will give the input, the context, the word letter is used in this sentence in the context of Rama is writing. So the context will give us an input and the letter will give us an output. So when you say that, when you give the context to the artificial neural network, it should predict the word letter actually. Okay, so when you train it, I mean, this is actually the word to vector. That vector is a byproduct. We will have a model. That is usually machine learning, artificial neural networks have been used for getting a model, trained model. But this is a byproduct. See, for example, you have weights. I mean, you know how neural network works. We'll start with a random set of weights, and finally, when it is converging to our desired form, there will be a vector of weights actually. So you take these vectors, these weights, and form it as a vector. So how many hidden neurons you use in the hidden letter depends on the dimensionality of the vector. We can make it 3-dimensional, 4-dimensional, even higher. So letters, this word can be converted to vector. Once you have a vector like this, you can add. So people have tried like this. Washington is the capital city of USA. Then if you give like that, Washington plus USA, in which you can subtract that USA, that from that knowledge you can subtract that USA and add India, then the system will predict Delhi, predict Delhi. So this is possible, and this has been effectively utilized. In a very recent publication in Nature, they came up with a new material, anti-ferromagnetic material, using these techniques. They have used around 5 lakhs abstracts in material science. 5 lakhs abstracts in material science they put into the system, word to vector format, and then they could add and subtract words like ferromagnetic and this, and it came up with a anti-ferromagnetic new material, so it's very recent development and people are trying with that. Okay, so this is what I wanted to say. So we recently are trying with this kind of thing. We are particularly concentrating on solar energy materials. The percentage of conversion energy, how much percentage of sunlight can be converted into electricity, is pretty low. There is a limitation with the current system like perovskite. Now people are coming with organic molecules like pyrolytic. So we are trying to get a better organic molecule using this one with the existing knowledge right now. We are trying that. Initially it is promising results we are getting. We are working on that. Okay, thank you very much.
Thank you so much, sir. Thank you for providing us insights on the use of digital technologies in knowledge discovery. Thank you so much. And now let's hear from the representatives from IRO Technologies Private Limited. I request them to share their experiences and share their technologies. Please.
Yeah, hi everyone. Hello, I am Ashwati from IRO Technologies. So we are a marine robotics company into the design and manufacturing of industrial grade ROVs. Our product is used for the asset inspections of dams, bridges, ships, etc. We are a company funded by GAIL and BPCL, and we have so far worked with some of the prestigious organizations like Indian Coast Guard, DRDO Labs, Tata Power, KCB, etc. So traditionally, these underwater inspections are mainly done by divers, which is a very time-consuming process, as a diver take 2 to 3 hours of operation. And while if he occurs any problem, we'll have to end up calling another diver to complete the operation. So we at IRO eliminate these divers with an equipment which is more safe and efficient. And we also have a software platform where we provide software reports, which is easier to track and analyze later. So at IRO, we have developed underwater remotely operated vehicles ranging from tuna to turd. Tuna is India's first commercial underwater drone, which has an operational depth of around 100 meters, and it can withstand 2 knots of water current. And turd is an advanced version which go up to 200 meters, and it can withstand 4 knots of water current. They can be integrated with different payloads as per the operational requirements, like side scan sonars, imaging sonars, NDT equipments, etc. So our product gives live HD videos, and also it can work in extreme hostile water conditions, as they are equipped with low light HD cameras and 6,000 to 9,000 luminous lighting. We have an internal battery which gives 1 to 2 hours of endurance, and also it can be externally powered, which gives 5 to 6 hours of operation. It is extremely portable and safe because there's no human risk involved in the operation, and it is very user friendly. And we have so far completed 40 plus projects, and we have an industrial grade patent. We also have a software processing and reporting platform, which is an integrated solution for asset inspection. So what happens is while we take videos and photos underwater, these images can lose its clarity due to the water turbidity, haziness, etc. So we use machine learning technologies to enhance these images and provide better solutions. And also, like while we take photos, a person has to sit through and analyze data and understand where the defects are. So we make a software report, which is data analytics enabled and easy to interpret and locate defects and anomalies. It is highly appreciated by clients because more than eliminating the time and process, it also can be referred at multiple times for rehabilitation and reconstruction works. So our vision is to make underwater surveillance smart and efficient, and we are continuously working for it. Along with the IDEX project, we are working on an autonomous underwater vehicle, which is mainly for defense applications and search and rescue operations. We are also working on an autonomous surface vehicle, which is an alternative for traditional diesel boats, and it is an environment-friendly equipment. It finds application in hydrographic surveys, water quality detection, pond and lake cleaning, detection of underwater objects, etc. And we're also working on different specifications to ROV. One such specification is a long-range ROV. It is for a long-range tunnel, duct or pipeline, etc. The operational range is around 2 kilometers for this new feature. And integrating a side scan or a profiling sonar will help in the entire mapping of a tunnel or a duct. So we have been awarded by different organizations like Indian Technology Board and National Startup Award. We are supported by the Maker Village and KSUM, Kerala Startup Mission. So this is our team. Our CTO was earlier working with National Institute of Ocean Technology, where he was a project scientist on onboard ships. And our CEO was working with Samsung and Gray Robotics. Both of them are IIT alumni. Thank you. We would like to thank Kerala State Council for Science, Technology and Environment for giving us this opportunity. Yeah. Any questions?
Thank you so much, Ashwati. Thank you so much for sharing your details of your technology. Thank you. Any representative from International Virtual Assistance Private Limited? Because we are unable to connect them. If not, we have reached the conclusion of this program. Now I invite Dr. Sharon BM, the scientist of KCST, to propose the vote of thanks. Over to you, Sharon.
Thank you, Sharika. Most respected Professor KP Sudhir, Executive Vice President KCST, Dr. Pradeep Kumar, Member Secretary KCST, our distinguished guests, Dr. A.V. Rahul, Professor B.J. Alapad, Dr. V.R. Sinija, Dr. A.P. James, Dr. K. Satish Kumar, representative from IROV, Dr. Devapriya Datta, Dr. Rashmi Sharma, the directors and scientists of R&D institutions, my senior colleagues and distinguished participants. This is the 9th program of the series of programs being organized as part of Vigyan Utsav and on the theme Future Technologies, a topic of high contemporary relevance. I consider it as a privilege for attending this program. And moving on to my duty, I profusely thank on behalf of DST and KSCSTE, Professor K.P. Sudhir, our Executive Vice President, for all the support and guidance in organizing the program meticulously. Sincere thanks to Dr. S. Pradeep Kumar, the Member Secretary KSCSTE, who is also the General Coordinator of the program, for all his efforts in the smooth conduct of the program. On behalf of KSCSTE and DST, I express my sincere gratitude to Dr. A.V. Rahul, who has joined us today and enlightened us with a keynote address. I sincerely thank on behalf of KSCSTE and DST, Professor B.J. Alapat, Professor Dr. V.R. Sinija, Dr. A.P. James, and Dr. K. Satish Kumar for sharing valuable insights into future technologies that will gain momentum in the accelerating world. I also extend my sincere gratitude towards Ashwati from IROV Technologies for sharing the experiences on their entrepreneurial journey. I wholeheartedly thank my colleague Sri Arjun Prasad, scientist at KCST, for his meticulous efforts in coordinating the conduct of the program and also for detailing the initiatives of KCST and Kerala State with regard to future technologies. Our sincere thanks to Department of Science and Technology, Government of India, Dr. Devapriya Datta, Dr. Rashmi Sharma, Dr. Ravikant Prajapati, and Dr. Mukund for all the guidance and support. Our gratitude to the officials of different S&T councils for joining the program, and special thanks to Karnataka S&T Council for the necessary directions and guidance. On behalf of DST and KCST, I thank the directors and scientists of various R&D institutions and the KCST headquarters for joining us. My sincere thanks to the scientists and administrative staff of KCST headquarters. Thanks to the technical team at KCST, the Information Systems Division, for managing the online platform effectively. I sincerely thank all the distinguished participants for their wonderful participation. I am sure you had a very fruitful time listening to the distinguished experts, and all of us got a good taste of future technologies which are relevant to the country and the state. Thank you all. Thank you one and all.
Thank you, Sharon. We now conclude the program. We'll meet you with the next theme next month. Thank you. Now, National Anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे